How was your Sub-Zero experience?
It was fun. Yeah, I mean,
Did you stay up the whole night? I know it was really late for you.
no, I didn't stay up the whole night. We are live now, just so you know.
Oh, sure.
Hey everyone. Yeah,
Hey,
no
everyone.
worries. I love starting off with a little casual conversation. So Sean's asking me about how Sub-Zero was for me. Sean is located in, Central European time. I'm way over on the other side of the world in Pacific time. So what I did for Sub-Zero, my talk started at 3:55. So I think 3:55 a.m. So I set my alarm for like 2:30. Yeah, set my alarm for 2:30 in the morning. Of course, like I woke up at 1. I couldn't sleep. I was like too like nervous, excited, whatever. And then yeah, no, I was just up until the event was over and for a couple hours after, and then kind of
Yeah.
crashed. It was a bit of a rough day, but it was fun. There was enough energy to keep me going.
Yeah. Cool.
Did let's ask a poll in the we have this poll feature in Crowdcast, so I'm going to ask a question. Did you attend Sub-Zero?
Yeah, give me one
Let's
second.
see.
Actually, I'm gonna wear my tie-dye shirt. I feel like you're giving
Okay.
me good vibes here, and
Yeah.
I want to match you.
Yeah, totally. We got time. All right. So I asked a question there. Did you attend Sub-Zero? And then let's go ahead and do another one. If you attended Sub-Zero, what did you think?
Right.
Can we only do like
More
oh,
fun.
right, because you guys okay, no, I'm not going to do that one. Because you guys made tie-dye shirts at the parody
Yeah.
offices, right?
Exactly. This is a custom-made tie-dye parody shirt.
That's super cool. Yeah.
Yeah.
Not only do I have to like wake up really early for conferences and stuff, but I miss all the fun office events that occur at the Berlin
Yeah. Well,
office.
I mean, I'm certain that once the COVID stuff dials down, you will make you a trip to the office.
Yes, definitely. I'm very much
Yeah.
looking forward to
Have
that.
you been to Berlin before?
I have been to Berlin once before.
Amazing. Yeah.
In 2010. It was a lot of fun. Yeah. Definitely hoping to go back sometime soon. So let's go ahead and kick things off. It seems like we have some good attendance already, which is great to see. And it also seems like based on the poll, a lot of people were at Sub-Zero. We have 8 people that were at Sub-Zero and 1 person who was not. So in case you're one of the people who wasn't at Sub-Zero, joining me today is Sean Trebrizi. He's a core developer here at Parody. And at Sub-Zero, our developer conference on last Thursday, he presented a really awesome presentation on some runtime benchmarking capabilities that he's developed. And there's a lot to talk about runtime benchmarking. And so today what we're going to do is kind of pick up where Sean left off to Sub-Zero, maybe do a little recap, and then continue that discussion. So without further ado, I'm going to go on mute and hand it over to you, Sean.
So I'm going to share my screen, and let's make sure people can see my screen. Yep, looks good.
Sean, while you're getting set up, just a reminder, there is the Ask a Question section there. It's different from the chat box. Please use the chat box to interact with one another. And if you have a question for Sean, use the Ask a Question box.
For sure. And then I'll be monitoring that kind of stuff too. So yeah, so I gave a presentation on benchmarking at Sub-Zero, but I think my time was a little bit short and the content I want to talk about was very long. So I didn't quite get through all of it. I want to really quickly, if in chat, if anyone specifically has not seen my presentation, just say I, and I will make an effort to go through the whole thing. But if literally no one says otherwise, maybe we could just skim over the parts that I've already talked about and just kind of jump back into where I was going, because then we can do a lot more kind of in-person examples, which I think is more informative to the everyday developing experience. So if you haven't seen this, why don't you say anything into chat? And you don't, and also, and I'm not putting you on the spot like this. You won't cause any problems. I just want to know, like, literally, if everyone's seen it, right, then it doesn't make sense. But I'm very happy to go over any content again.
And Sean, maybe while we wait for some, Joshy's asking to skim the stuff you present. I think that's a good idea. And also, Will has a really great question in the Ask a Question box. And you may be covering this, but it's kind of just straightforward. Like, why do we benchmark the runtime? And so that's a great thing to talk about.
Yeah, and I covered that in my slides. So let's let me go through it then. And if you still have that question at the end, then we can talk about it again. But yeah, so I guess
and Sean, maybe if you could just let me know when you're answering that, I'll hit the start answering button, and then I can stop. Yeah, cool.
Sure. Yeah, so anyway, my name is Sean. I work at Parity. I build a lot of the runtime stuff, and I actually spent a long time kind of developing this kind of end-to-end benchmarking pipeline. And yeah, we're going to go into it. So a quick overview. So what are we talking about in this talk, and hopefully more actual examples in the end, is a quick recap of what weights are. We're going to dive into the actual benchmarking process to kind of explain what the process does. Then I'm going to go over some of the learnings that we learned throughout the development. This is something I couldn't touch on the Sub-Zero talk, and then some of the best practices. And these are things that I think we can reiterate in some examples here. So really quickly, the thing you'll hear very commonly together is weights and benchmarking. So what is weight? Weight is basically a representation of block execution time. So on a standard blockchain, let's take a chain that you just build with Substrate. By default, it has kind of a target block time of like around 6 seconds or so, and it's kind of important to keep the chain kind of rhythm going. Like, I mean, I think almost every blockchain has its own target block time to kind of keep the blocks at an even pace. And basically, weight is another representation of this time. Specifically, it's a representation that we can use to make sure how much functions or execution or just things that we can do in the window we have for executing a block. And so literally in Substrate, we have it right now hard-coded that 10 to the 12 weight is equal to 1 second, or 1,000 weight is equal to 1 nanosecond. One little tidbit here actually is, originally we were designing it so that 1 weight equals 1 nanosecond, because 1 nanosecond is about as fast as you can get in terms of measuring on a computer. But we had been asked by the contracts team to actually make it so that we have some extra zeros to work with, because some of the contract functionality may be like sub-nanosecond measurement type stuff. So we add an extra 1,000 for them, and this is why we have 10 to the 12 instead of 10 to the 9, just a little tidbit. But anyway, this is just representation. So when we talk about weight, when we talk about the weight of a function, what we're really saying is how long it takes to execute. Now there's a caveat here, right? I'll get to the caveat in a second, but let's take a quick look at the overall kind of block thing. So as I mentioned, on a Substrate blockchain, you might have like 6 seconds to work with in between blocks, but you can't spend the entire 6 seconds doing computation. There are other parts of the block synchronization process, like gossiping the block to other peers, importing the block if you're a peer, getting it ready for you to produce the next block, all that kind of stuff, right? And so of this 6 second window, we actually have a much smaller fraction of time. Here we have 2 seconds really to work with in terms of actual execution. Now, this is, of course, all configurable, but on Polkadot, for example, these are the exact numbers that we have a 6 second block time on Polkadot, and we allocate 2 seconds of that 6 seconds for actually doing extrinsics and transactions. And then in that time is where we have to fit in all the things to be familiar with when you're developing your runtime. Things like the onInitialize function, extrinsics, onFinalize, and have a block import overhead. And of course, the extrinsics themselves have some kind of base weight to actually dispatch the functions and get them started. And then the actual extrinsic itself, depending on what kind of functionality you write, may have a different time it takes to execute all these things. So all of this we have to fit into the 2 second window to make sure, hey, we can get these blocks running kind of safely on the network. So then again, I was kind of alluding to the fact that, there's a caveat here. Well, 1 second of compute on different computers isn't the same thing. On my MacBook Pro versus, a supercomputer versus your phone, 1 second of compute is different. And so when we talk about weight, again, it's a representation of time, but it's a representation of time with a lot of assumptions about what processor you're using, kind of memory you have, the hard drive you're using, the operating system drivers, literal everything you can imagine that could affect the performance of executing your blockchain is wrapped up into the assumption about weight. And so when we say the weight of a function is, let's say, 1 million, which means it's 1,000 nanoseconds, we're really saying is it's 1 million given these conditions, given these assumptions about your computer hardware. And of course, we know that over time, things will evolve and change. Naturally, the Rust compiler changes, and that could affect the performance, hopefully for the positive. Computers improve, so as time goes on, the weights of your blockchain are definitely going to change. And in general, one of the things people ask all the time is things about throughput and about how I guess like, they always ask like when they hear about a new blockchain, like how many transactions per second can you get? And I always find this a little bit of a kind of a silly question because, depending on what hardware you select, what kind of assumptions you're making, the number is going to change a lot, right? So like if you assume that everyone has a supercomputer running your blockchain, you probably could achieve, tens of thousands of transactions per second. But you need to make sure that have reasonable assumptions about your hardware so that it's open for all validators of all different types to be able to participate in your network. And then that, of course, improves the decentralization nature of the blockchain. And of course, the more validators that can produce blocks in your blockchain, kind of the more competitive your blockchain is, and the kind of the more secure it will get as a result. And yeah, so these are kind of things you have to keep in mind when doing all of this process. So,
Sean, we do actually have a question about this in particular. What is the baseline CPU performance, for example, 6-second block time and 1,000 wait?
Yeah, so those two numbers don't quite make sense to me, but I can tell you that that Polkadot has a spec machine. I think this is like an i7 4.2 gigahertz quad core, or 8 core. That number, of course, it doesn't matter because the runtime is single threaded right now. Actually, I don't think I have quickly the specifications. Actually, I might be able to get it real quick. Let me if you can still see my screen, I'm going to jump over to graph benchmarks.
Yep. We can see your screen. And while you're doing that, Sean, I'm just going to kind of like muse for a second here as you're talking about this stuff. Like it's interesting to me. Like basically what you're talking about is defining a unit of measurement. And so in this case, we're using weight weight does not refer to like a unit of heaviness. It refers to a unit of time, it sounds like in this case. And then just like there is a like kilogram, the capital K kilogram that sits in some laboratory in the UK or something that is like the canonical representation of what a kilogram is. We have defined some environment that we use to deterministically calculate these weights.
Well, actually, see, I think you're 50% right. In the sense that weight is actually a measure of the heaviness. So the reason why we distinguish weight between time is because, again, that time assumes something about what hardware you're running on. Weight doesn't make that assumption. So when you generate the weights for your computer, you're running it on, using these assumptions, and then it generates for you basically the timings. But I guess the distinction here is that weight is a unit of time, but it's attached to it a like variable assumption. So we could both have the same pallet, but my weight could be different than your weight because my assumptions are different than your assumptions. And this is why we have a different unit here. It's like the unit kind of wraps time plus assumption, if that makes sense.
And that assumption is that canonical set of hardware that we talked about.
Yeah, exactly. But none of our framework pushes our assumptions onto you. So I think this is the important part I'm showing you here a screen of what we use to benchmark Polkadot and default Substrate and Kusama and like all that. This is the machine. And we chose this machine because it's like high-end consumer hardware. Like this isn't only server specs. This is something that a human could have, but these are quite high specifications in terms of this is like a gaming computer, right? But we don't make this assumption for your blockchain. Your blockchain can have, could be running on a Raspberry Pi for all we care. When you run the benchmarking system, we'll generate weights for your assumptions. Yeah.
Nice. Thank you for that.
Yeah. So that's the information there about what we use for Polkadot. Let's go back to present. Let's just go big screen here.
Marco, I hope that answered your question. Feel free to ask any follow-ups if you have some more. Yep.
Okay, so then I want to jump really quickly into the benchmarking framework. I won't talk too much about this because I think we can go by example, but there are a few pieces that we have to make it all work. To start, we should talk about the plan. So the general plan was to do empirical measurements. So I think there are, when you talk about different blockchains and how they approach kind of measuring the compute time of the different functions, there's a few different ways you can do it. One approach might be a more theoretical approach where maybe you're counting different operations, you're measuring it kind of on a point-by-point basis, and then accumulating, okay, this is the overall theoretical time it should take. We, on the other hand, are using empirical measurements. And this is a lot more efficient in general because you don't have to have this overhead of kind of doing gas metering. And when we can have empirical measurements, maybe take a lot of the overhead out of the way, and we can just tell you before you even run the function how much it should cost. You can kind of think of a benchmark in that case as a black box. We give it a bunch of inputs and we empirically measure how long did it take. And we want to do this over a bunch of different inputs to figure out, okay, what are the timings, right? Another thing is that we have to assume, because we're doing the empirical measurement here, we have to basically assume worst case scenario. This black box, or I guess all of benchmarking in general, is all about protecting your chain and making sure that it's resilient to potential attacks on this kind of open platform, right? So when we do this empirical measurement, we also add into this black box a bunch of assumptions that are kind of like the worst case scenario. Like what is the worst thing that could happen in this black box given these inputs? And then that's the timing we pick. So it's not the primary goal of this benchmarking to give you the best possible time pushing the limits of what's safe. It's actually the primary goal of benchmarking is to make sure that your runtime, no matter what situation in the real world it's in, will be safe. And then the secondary goal is to give you a bunch of utilities and tools so that you can optimize that time and basically lower it so that you can maximize throughput. But that's a secondary goal. And I will say that to be frankly honest, our benchmarking framework is not perfect. Like our results kind of showed at the end of the benchmarking that we were about 100% over the estimate of what the actual time was when we're running in kind of a normal conditions. And that, that's not great. We want to, in general, get it as close as we can to, our benchmarking actually measuring the actual time it would take. But that being said, in worst case scenarios, we know that the weights we picked will be safe. And this is what's most important for your chain. Okay, so that's the plan. How we're going to do this basically is just running the function. So basically, we just set up some macro, and I know that you all love macros, having built on Substrate, right? We basically set up some macros that allow you to define some function, basically writing a test, execute an extrinsic, and then get a timing out of that. And the macro is meant to look like writing a test. So like, you set up some state, you run the function, and you verify the final state. But in this case, the test, instead of failing, if you write like a failing test, must succeed. And it hopefully succeeds given the certain conditions that you want and to test for in this worst case scenario. So that's what the macro provides. And then once we get these timings, built into the framework is this linear regression analysis. So basically, given some function, a function can have a bunch of different inputs, like you can imagine that it will change based off of, 3 or more variables or, whatever. We are going to get a bunch of different inputs, tweaking these different variables, and then we're going to get a bunch of data points. And then we basically want to find, okay, what are the fitting of the curve for these data points so that we can basically figure out that, given 1,000 data points, we can actually infer what every single possible input, what the timing should look like, right? One of the assumptions we make here is that all of the benchmarks and all of the runtime in general should be linear complexity. Now, I hopefully shouldn't need to go too big into, the problems of introducing, super linear complexity into your runtime. But in general, if you have anything that's like n squared complexity, and the user can adjust what that n is kind of arbitrarily, you're basically allowing your runtime to be attacked, because at some value of n, your extrinsic will not be callable anymore. And at some value of n, you're basically allowing one user to basically take up all the compute time. So it's kind of important that if you have anything that's super linear, it's not saying that you can't have it, but if you have anything that's super linear, it has to be limited in window, like it can't be unbounded. But in general, the framework assumes things like linear complexity. And actually, I wonder if you can imagine with my mouse. Can you see my mouse here? Yeah. So if you can imagine some kind of super linear function, it might have a kind of a steep curve like that. As long as it's bounded, we can know what the top bound would be, right? So then we can put a line over that function where every single point on this line is over this exponential curve, right? And so in that case, our linear fitting would still be safe in the worst case scenario. It's only when we don't know when this bound is and this exponential graph passes this linear graph, that's when our function would actually take more time than our weight would expect. And this is where things are bad. So you can see that this linear fitting actually works quite well, even in these bounded scenarios, but definitely you can't have unbounded superlinear complexity. I'm gonna take a break real quick, make sure that makes sense, right? Imagine just again, an exponential curve underneath this line is still okay.
I don't have any questions on this, Sean, because in general, this kind of stuff is like not where my head is at. So I don't see any questions about this in particular in the question box, but Will has got some really, really good questions in there for you. So I don't know if you just want to. What's that?
Sorry, this is the why do you want to benchmark the runtime thing?
No, there's a few other ones in there. So I don't know if you just want to like quickly review them to see if, just so you know if like there's a good time for you to properly address them.
Sure. Okay, so Will asks, are weights only relevant to block production or block planization as well? How do multiple substrate chains with different weights affect execution in a pair thread? Okay, so let's start with the first question. So actually the weights are relevant. So the weight that we care about is relevant in block import. So you as a person running a blockchain, you might have a computer way faster or way slower than our specification. And it's kind of on you at that point to make your block in time. Like, if you want to have a slow computer, you can do it. You might just miss a bunch of blocks. This is shitty for only you. What we care about is the one thing we know every blockchain has to do. Every blockchain has to import a new block. So when I produce a block and I say this block is within weight, it is telling the network, hey, as long as you're running the standard hardware, you should be able to import this block without issue. And this is what's critical, because if we allow someone to make a block that's overweight, and everyone on the network is spending a lot of time importing that block and running behind, and then there's some malicious actor who has a fast computer and making everything work well, this is where the attack happens. So we care about block import in the weights. It's a great question. And then how do multiple substrate chains with different weights affect execution in a pair thread? Okay, let me figure this out. I think that we will probably force pair threads to have the same block execution limits or like weight situation as Polkadot. I don't know if we've actually figured out the full weight story there yet, but my guess is that all of the pair threads will have to kind of work under what the Polkadot assumed weight umbrella would be. But that is a good question, and I might be wrong. My screen is too small. Current speaker. Yeah, I can't make the presentation. Okay, I can make it a little bigger like this, but it might cut off some stuff. Like I mean, it's literally my entire screen right now. So
yeah, I agree, Sean. I don't know how that looks a little bit better. Would it be possible for us to provide these slides to people so they can review them afterwards?
Yeah.
Cool.
And I'll provide that slide. Okay, so the other question is for processing, which matters more, clock speed or number of cores? So definitely it's clock speed. So number of cores, again, the runtime in general is single-threaded. Actually, I saw a PR recently, which is going to maybe introduce parallel execution in the runtime, which is very cool. But for now, it's all single-threaded. And beyond, there definitely will be a performance increase from a single-core computer to a dual-core computer, because of course, there are other things running on a computer to make your operating system run. But I think once you get from like dual-core to 4-core or 4-core to 8-core, like there's not going to be much difference. It's about the single-threaded throughput that we care about. Okay, I'm going to keep going if that's okay. So anyway, multiple linear regression analysis. So we have that talking about. So that's one of the functionalities. Oh, that got a lot worse. Okay, and then benchmarking the CLI. So then of course we wrap everything in this nice CLI. Basically, one of the fundamental things we want to do about benchmarking is make it so that it was all automatable. And so basically we wrap kind of the process of benchmarking into our CLI, so you can just run some process and we'll automatically generate weights for you. And then finally, the weights get auto-generated and it's written into a Rust file. So basically the idea is that you can basically have a bot commit the output of the CLI into your repo, and it will just compile and work. I mean, it's not perfect like that yet. I mean, I think, given enough human hours, we could probably actually get it to that point. But, basically we give you a Rust file and we say, hey, this is like valid Rust, like just import it and use it. And for the most part, for people who are using, for example, pallets that already exist, it will be that easy. It's a little bit more complex if you're a pallet writer. You need to kind of know what the format looks like to kind of set it up to begin with. But, that's a small potatoes. Anyway, so let's jump into the deep dive. This is the core piece of benchmarking. This is where we're going to talk about the actual process. So the benchmarking process. Basically, there are 10 steps here that we go through every time you run a benchmark. The first thing we do is actually whitelist any known DB keys. Actually, for references, real quick, if you want to follow along, this is all in this benchmarking source librs file, this function called run benchmark. I'm basically just reading to you what this code does. Yeah, so first thing we do is actually whitelist some known DB keys. So basically, one of the things that you should know kind of upfront about benchmarking and upfront about kind of about Substrate is that accessing the database is heavy. It's probably one of the heaviest things you can do in Substrate. To give you context, the logic for doing a balance transfer is about 50 microseconds, whereas doing a single storage read is like 25 microseconds, something like that. So it's really significant amount of time. So part of the benchmarking process actually specially handles database reads and writes, and part of this involves making sure that we're not going to be over counting writes and reads that you're not responsible for in your extrinsic. And this is again about tweaking kind of the optimization here. So we know that there are certain storage items that are accessed every single block, like the block number. Like every time you make a new block, you need to push what the new block number is. So if your chain or if your extrinsic is trying to read the block number or write the block number or whatever, we already we say that this is free for you because it's already kind of taken care of. We already have read that value from the low-level Merkle tree. It lives now in this kind of overlay, this memory overlay, and accessing this is very cheap. And in fact, we actually take this into account when we run our benchmarks because our benchmarks are actually run using a memory database. So this is basically the first step is basically what are the things in your chain that are accessed all the time, and we whitelist them. And you can actually even in a benchmark dynamically whitelist new keys. So if you know in your benchmark that these keys should be whitelisted, we allow you to do that. But that's the first thing we do. We whitelist the keys in the database. And then we select the components we want to benchmark. So basically, we assume that every function has some variables which can manipulate the timing of that function. In this case, we have 3 variables, x, y, and z. And these variables can have a range of values. It can be, let's say, members in a group. It can be from 0 members to 100 members. And 100 members is where we have the kind of the hard cap in our runtime. Or it could be the size of the payload or something like that, right? Or like the size of a vector. It can be 0 elements to 100 elements. And then we have some kind of limit in the runtime that says, okay, well, we won't support more than these number of elements. And so we basically allow you to find those different components and the ranges. And we generate this table here, which basically measures kind of tweaking each of these different components across the range. So what we do here is specifically we take one component, we modify that one over its range, and we keep the other components at its maximum value. Again, we're assuming worst case scenario is when these components are at their max value. And so you can see here, we basically generate a table which says here, all of these columns is one input into our benchmark, which we want to get a data point for. Yeah, and then basically, we have some step sizes. I'll show you that kind of later when we actually do it ourselves. Then we actually run the benchmark, and it's kind of as simple as setting it up to begin with. So given these inputs, your benchmarking logic can basically adjust the initial state. So if the benchmarking stuff we want to measure is here, where we have, let's say, one user, there's a group of 10 people, and they have, one asset on the chain, right? Given these inputs, we want to set up the state. So we have some kind of loop that says, okay, well, if X is 1, we create one user. If Y is 10, then we create, 10 groups in this member, whatever. And we set up the initial state, and we push it. This is just like you would write for a test. And then basically we execute the extrinsic. So given some initial states, we actually run that extrinsic on that state, and then we get a positive output. Like we say, hey, this extrinsic ran. And basically before we run the extrinsic, we get the system time. We run the extrinsic, and we get the system time again. And then this difference in system time is our benchmark. This is how long it took to execute this function. This is the empirical measurement of this black box, right? And then finally, at the end, we count the number of DB reads and writes. So we use a special kind of database overlay in benchmarking. One, it's not a real database. We don't actually write to your hard disk. We actually write to an in-memory database, and I kind of mentioned this before. And the way we can do that, the reason why we can do that is because we actually count the number of keys that we're modifying throughout the entire benchmark. Like every single key you touch, we measure it. And then we give you a report. We say that, okay, well, here are all the keys you touched. And so when you're writing your weights, you can say, okay, well, this is how long it took to run the extrinsic logic. This is how many keys that you touched. And there's some kind of weight associated with reading and writing a key. And this combined together will be the overall weight for your chain. And of course, we record that data and we give it back to you, and we kind of process it and we give you back the results. Let me take a quick pause because I just went through a lot of stuff.
Lots of good questions in the question box, for sure.
So there's one here from Gabriel. Should we whitelist writes and reads done in uninitialized functions and every pallet in our runtime? Yeah, I mean, it depends on how, the weights. You can kind of go as deep as you want to go. In general, yeah, if you know that your blockchain makes an assumption that every single uninitialized, there's some kind of item that all of your pallets are touching, definitely you'll see a big improvement by whitelisting that benchmark. And you can actually whitelist that kind of storage item at the runtime level. So we actually have a whitelist at the runtime where it says, like, for every benchmark, make an assumption about these storage items. But then also if there are just some extrinsics where, let's say you have an uninitialized writes an item, and on finalize cleans up that item. So that item never actually gets committed to storage. It's kind of transient in the case, right? My on finalize benchmark would, my on initialize and on finalize benchmark would basically whitelist that storage item because it never actually gets read or written to. It's just kind of transient in nature. So I would benchmark it just for that benchmark instead of doing it for the entire runtime, if that makes sense. So that was that question. So how to whitelist DB keys? I will hopefully show you that an example when we actually do some stuff, but it's quite simple. Basically, the simplest thing you could do actually is when you generate a storage item into closed storage, there's actually an API called like get hashed key or something like that. And if you call this, it gives you the key, and you just call this add to whitelist, and that's as simple as that. Let me see if I can show that real quick. So storage map. Here's an example. Yeah, and there's this thing you can see here.
We can't screen right now, Sean. Are you trying to show your screen?
Yeah, is it not working?
All we see is the presentation, or at least that's all I see. My Crowdcast could be running slow. That's happened before.
But my audio is right, huh?
Your audio is right, but all I see is the benchmarking process slide.
That's crazy. Okay, that's not good. Well, I guess hopefully my screen isn't frozen. Oh yeah, it's been frozen the whole time. I mean, because I still see on the Crowdcast, I'm on the let's walk through steps of the benchmark, and I actually had text for each step in the benchmark. So let me maybe stop sharing my screen and try sharing it again. Good call. Okay, let's.
I think Joshy's right. It's a Dan thing. Crowdcast has not been liking me lately.
Well.
Apologies for that.
Yeah, hopefully you can resolve your issues with Crowdcast. Okay, so we're back. Yes, I see stuff happening. So anyway, you didn't miss much text. I mean, I basically explained the steps of the run, but I want to show you here, basically in the storage map, there's this function hashed key for, and it gets the storage key for a specific key value thing. So it could be as simple as basically getting this key and then using it directly. And this key is just evacuate. So it's something as simple as that. But I can show you more details when we actually jump into the benchmarking. Hopefully you can see my presentation now again. Oh, wow, it really doesn't like it. Yeah, it's not changing the screen.
I think it's something that might only affect you when you're on. I don't know. Alex is saying whether or not it's working. For me, I still see the rust docs.
Yeah, and that's trying to stop. Okay, let me stop one more time and start one more time. And if not, then we're gonna have to figure out something better. Okay, let's try the entire screen. Yeah. Okay, I think that might have been my fault. I might have been clicking just to present one window instead of the entire screen. Oh my gosh. If that's the case, I'm really sorry. Okay.
It's my bad luck bleeding over to you. Don't take it personally. It's all me.
Cool. Okay. In this case, oh no, but yeah. See, I just full screened my screen and it doesn't show. So it's definitely it's like oh here. Oh okay. It's changing. Something changed. Okay, something is happening. Okay, so it's working. I think for some reason it seems like it only changes based off of me doing some action. But okay, anyway, so I want to show you here. So this is kind of what the benchmarking process might look like. So you can see here, again, we have this whole table of inputs. We basically push those inputs into the benchmark. We actually repeat the benchmark a bunch of times. And that's why you can see that there are some, for every point that we're benchmarking, we benchmark it multiple times, of course, because there might be like outliers, might be like, some random fluke in your CPU. And then we get these data points, and then we create a bunch of graphs. And you can see here with 3 components, what we're actually looking is to create 3 different linear graphs describing basically the coefficient, the linear coefficient, which affects the benchmark for this component. And we can generate a formula here that says, well, the time is equal to some, ax plus by plus cz plus some constant. And yeah, that's basically the simplicity of the benchmark. What we do here is really just recreate this weight formula. And from that, given the inputs, we can tell you how long it takes, and we can tell you the weight of the formula. So it's that simple. Okay, so if I change Windows, does it do anything? No. Darn it. I really have no idea what I can do to let you keep seeing my screen, except for restarting each time. I'm going to close video and try again. I have entire screen. Allow. Okay, let's try again. Okay, so example benchmark. Yeah, okay, we can see it here. Let me make it big again. Okay, so there's an identity palette. This is what we're going to be using to do an example with. And I just want to give you a quick overview of what the identity palette does. The identity palette is a way for you to basically store on-chain some information about yourself. Of course, it's all optional, but if you want to, you can put things like your name, your email, your Twitter on the blockchain. And this is useful because we can use it in the UI and basically kind of show things like, I'm a council member on Polkadot, and you can see my information on there, and it kind of gives you at least a name to the user account. And then in the identity palette, we have this kind of registrar-based judgment system. And basically, an identity can be judged by multiple different registrars. Of course, the identity itself can have a variable number of information. And the identities can also have these things called sub-accounts, where basically, if I get my identity registered, but I have a bunch of different accounts that I'm using to, work with the blockchain, I can actually kind of have these other sub-accounts inherit my identity. And hopefully, you're kind of seeing here that there's a lot of variability in the identity palette. And so when we do benchmarking, we need to take into account, okay, what will happen in the timings based off of how many registrars there are, how many sub-identities you have, how many information items you have, and this all kind of stuff. So these are the components that we care about kind of when we're benchmarking the identity palette. And so my next screen, yeah, you can see it. Okay, so let's look at the kill identity extrinsic. So basically, I'm going to walk through the steps here of kind of looking at this extrinsic and evaluating kind of what when I'm benchmarking it. I just want to look at it first and kind of understand what it does and what are the pieces I'm going to need to tweak or measure in my benchmarking, right? So first, the first thing I noticed is that this benchmark has a configurable origin. It has this force origin, and this may not inherently cause anything that we need to benchmark, but it does mean that different blockchains, when they implement the identity palettes, may have different implementations of this force origin. For example, in one blockchain, it could be root. In another blockchain, it could be like 2/3 of council. Another blockchain could just be like one user. And so we need to make sure that when we run this, extrinsic, that we are always able to pass this test. And so in order to do this, we actually have to introduce into this ensure origin trait a special function, which is only testable during the feature runtime benchmarks, the successful origin. And this is, of course, not an origin that you want to, or a function you want to give access to normally. But for benchmarking, it's important that we be able to always return an origin that would pass the test. And so you as a person building benchmarks and designing kind of more complex systems with traits and functions may want to think about, okay, what are some kinds of functionality that you want to add behind this runtime benchmarks feature flag, which are needed for people to benchmark your runtime successfully, right?
Sean, I'm going to interject with a question
Sure.
That's been in the box for a little bit now that I think is kind of related. It says, when do we need mocks for our benchmarks?
Right. So just like when you run a test, you need a mock runtime to test your environment in. Benchmarking actually uses your real runtime as a mock. So when you run a benchmark, we run exactly how you've configured it in your actual production runtime. But we, of course, have a pipeline so that you can test your benchmarks without having to go and run your runtime directly. In that case, we will take advantage of the mock that you created for your test. So basically, the benchmarking pipeline will create a bunch of test functions, which you can just pop into a test, and it'll run your benchmark against the mock runtime that you've created for your test. But in general, you don't need to mock anything if you're just using a benchmark. Your mock is your actual runtime. That answers your question? Okay. So let me see if I can get the next slide showing on the screen. Holy crap, this is really unfortunate. It really seems like I need to like restart the presentation. Oh, no, okay, it was working. It's working now. Okay. So now we're looking at target. Okay, so now there are other parts of your runtime functionality, which are these hooks, these basically configurable traits, and you might see these kinds of things.
Actually, I'm sorry, Sean. I'm gonna interrupt you because Joshy had a question related to the other thing. What if this successful origin does very little computation, but his origin check is somewhat heavy?
Yeah. So again, of course, yours could be heavy. Your benchmarking it should not be that your origin check is variable. That's kind of complex, right? Like, and it's actually I talked about here in this other hook, that hooks in general can't be variable to the point where the benchmark writer doesn't know how to adjust their benchmark to do it. So imagine that I'm writing some pallets, and I give you some open-ended ability to add some traits or some functionality into it. Well, I, as the benchmark writer, can't know how you're going to write this function. So you as a person implementing a trait here should first assume that it's constant time. There are some ways where you could have a trait which is example dependent on the number of members. And it would be kind of obvious in my benchmarking that I would adjust number of members in my benchmarking. So you could write a hook which is variable depending on the number of members there. But that would have to be kind of explicitly stated in the palette that you're consuming in your runtime, that this palette supports for this function benchmarking where the number of members is variable for this hook. But in general, hooks like checking the origin or for example, doing a lookup here have to be constant time, because if they're not constant time, then basically we can't ensure that we're benchmarking it at the worst case scenario. But if your hook is, for example, very heavy, that's okay. I mean, it's going to suck for your extrinsic because it's going to be heavier. But again, because we run the benchmark in your actual runtime environment, it's doing the actual check. I mean, like we aren't cutting any corners here. You're actually running your extrinsic just like you would on a blockchain. We're just automating the whole setup process. Like, I mean, you almost could imagine running your blockchain with some kind of timing flag on, and then actually going and write, on your computer on Polkadot.js, submitting a bunch of transactions to give users accounts and all that kind of stuff, and then submitting the extrinsic and then timing it yourself. Like, you could do all that and you would probably get the same results we get, except we're just automating this all for you by basically, injecting all of this functionality through these benchmarking framework. So yeah, it's okay to have functions which are different. It's okay to have functions which are expensive. It will all be accounted for. It's important that there's a kind of a contract between the runtime developer and the person, or the palette developer and the person putting the palette into the runtime, that they are doing things which are sane with one another. And I assume that this will be a lot of documentation that will make sure that things are safe. So yeah, I mean, basically, I actually talked about what I want to talk about on this slide. So again, it's very easy to give users a hook, but it's important that, with great power comes great responsibility. This is a common thing in the runtime. You need to make sure that you understand the limitations of these hooks, and that you as a person implementing the runtime don't do things which would give you benchmark results, which would be wrong for your runtime. Because what ends up happening here is then maybe your blockchain is exploitable, right? It's attackable. That's bad. Okay, so then we can, you have basic lines like this. You can see here there are just some storage operations, and this is very average, right? We can see here that there will be some storage, take, which is a read and a write. And then we also have here another take. So the things, the things I would be thinking about, okay, well, look at these storage items. These objects themselves may have variability in size. So I need to make sure when I'm benchmarking the runtime that I'm taking into account the size of these things. So in this case, the identity of a user may have a variable number of fields and also a variable number of registrars with kind of votes on that object. So the more votes there are and the more fields there are, the larger the object will be. And that might influence the benchmarking. So I will look to, in my benchmarking, adjust those parameters because I'm obviously interacting with them. And then also, I can also look at the benchmark and kind of say, okay, well, I expect kind of 2 reads and writes at least here. The output of the benchmark should also give the same results.
Sean, I'd like to pause and just ask a little question. I think in some ways it's kind of intuitive that if you have like larger storage structures, it will somehow be more computationally intensive.
Yeah.
But I think it's like worth pointing out like exactly kind of how extreme that situation is when we're dealing with substrate storage.
Yeah, so the one thing I can talk about for sure, so I actually have a slide later which talks about the RocksDB. So every database themselves are going to have their own implementations about accessing data of different sizes. So you can imagine like as data gets bigger, especially on the powers of 2, there may be changes in how the database behaves in terms of fetching that data. And this is definitely very database specific. So we actually found that RocksDB itself was actually very hard to predict, which is one of the reasons why we separated out database benchmarking from the actual extrinsic benchmarking. And I have a slide on that later, so we'll get to that in a little bit. So, but there is 100% with every database. Like if you're reading a 5 GB file or a 5 KB file or a 5 byte file, it's going to be a different amount of like kind of overhead onto the underlying logic to retrieve that file for you. So that's going to be one piece. The more important piece, which I think will affect more users, is the encoding decoding time. So all of these storage structures, when we're interacting with them in Rust, is normal like Rust bytes. But when we store it into our storage, it's actually scale encoded, right? And so between writing an item and reading an item, we need to do encoding and decoding of the bytes in storage and the Rust bytes that it expects. And so really when we're talking about overhead of the size of these objects, what we really care about is this encoding decoding time. And it's not only about the size of the objects, but also the complexity of the codec. Like there are more complex objects in scale codec. For example, you can think about like recursive objects, or you can think about compact encoded numbers, or you can think about all these other things, right? So it's not even about the size, but also the complexity of this of encoding and decoding these objects. But that's kind of where some of this overhead would come from. Now, you wouldn't expect it to be a lot, and in general it isn't. But again, you never know, and you always want to, of course, take into account when you can. Right?
It's kind of one of those situations where like it does become, when you're getting at this level of benchmarking and stuff, I think it does become somewhat important to become aware of the implementation, not just the interface, because it informs your benchmarking strategy, I would say. Yeah. Do you agree with that?
I mean, of course. I think that if you haven't seen my talk from 2 Sub-Zeros ago or whatever about storage, where I do a deep dive into storage, like unfortunately, yeah, like I am talking here with a lot of assumption about the knowledge you have about Substrate. And the honest truth is, if you want to be a good runtime developer and you want to write good benchmarks and good pallets, you need to have a deep understanding of how Substrate works, because you need to understand how Substrate could break or where the limitations are. And it's not that you should alone know these things from like the vacuum. Like, of course, myself, Dan, and others are there to help you and to share that information. But you can't, for example, just jump into runtime development and just take things for granted, where you could actually do this in a gas metering world. Like people who write bad contracts on Ethereum, they don't have to worry about what the code they write. The effect is that with gas metering, that no matter what they do, that everything is safe, because we're actually measuring in a theoretical limit on a point-by-point basis, right? But you, as a runtime developer, you can assign weights to your functions, and you are definitely within right to be wrong about what your weight is. You're definitely within right to have a bug in your benchmarking pipeline, and that bug could absolutely affect your palette and people who use your pallets. So what I would say is, again, the runtime development and blockchain development, as simple as we want to make it, and we want to make it for the new people to be able to play around with stuff. When you talk about releasing a multi-billion-dollar network out to the world, like, let's be honest, this is real stuff here, and you need to be careful, and you need to have a deep understanding. And this is where I expect, as time moves on, there will be teams of people, like an entire company of people or an entire company whose purpose is to go to runtime development teams, help them benchmark the runtime, help find, and audit their benchmarking systems, that kind of stuff. Like if you're someone who's looking for a company idea, maybe you don't have the idea for the blockchain, like maybe you could invest in learning about Substrate and then being that team that will help make sure that other blockchains who use Substrate are safe, right? But yeah, you need a deep understanding. So
yeah, and I think, it's not my intention here to like kind of scare people off or anything like that. I think one of the reasons why I bring this up is because one of the first pieces of advice that you ever gave to me when I was learning about Substrate was learn about storage. Start with storage. And that was really good advice. It helped me understand the scale codec. It helps me kind of more intuitively understand the things that you're talking about now. So this is kind of my way of, I guess, kind of resharing that advice, really understand storage. And then on another level, I think just this idea that like, as a software developer, I love living on layers of abstraction. That's how I maintain my sanity. But clearly when you're benchmarking, there becomes a time, it is a time where you kind of need to break that abstraction a little bit. You need to worry, okay, what is the actual hardware that this is running on? You need to worry about things like, how is my storage implemented? So benchmarking is a different mindset than development, from my point of view.
Sure. Yeah, I mean that's absolutely true, and then to really nail home that point about learning storage first. If you think about what a blockchain is, right? A blockchain is basically this. The funny joke is that it's just a really advanced database, like a distributed database or some kind of something like that, right? And so really at the core of the blockchain, what we care about is the storage of these items, right? And optimizing it and these Merkle trees and stuff like that. There is of course networking layers, consensus layers, all that kind of stuff, but I would say the average path for a runtime developer using Substrate doesn't really care about the networking layers, doesn't really care about the consensus stuff. They care mostly about storage and doing state transitions, and basically that's adjusting storage. So when we talk about starting with storage, you're really starting with the thing that you care about and adjust most frequently when doing the runtime. So yeah, so let's keep going. Let's talk about more storage stuff. So you can see here that in this kill identity logic, there's a loop here that will loop over and remove all the sub-identities. And so this is, in my mind, think about benchmarking, like, hey, this is a dangerous thing. Like if this loop didn't have an upper bound, users could be, deleting, a million items, and this would be really, really bad. So we need to set some kind of upper bound in our runtime logic, and also make sure that we check this upper bound in our benchmarking, right? Let's see if the screen changes. Yep. Okay. And then, of course, we see here there's some kind of currency operations. So this is like the currency is doing a slash operation. So this is actually in my identity palette calling into my balances palette, and the balances palette has its own logic for what it's going to do, right? So this is also similar to those hooks, right? And then I also have here a slashed trait. And what we do with the slash balance is we allow you to configure. So you could set it to treasury, you could just burn it, you could give it to a random user, something like that, right? And so all of this stuff is kind of configurable, like which palette you use for your currency and which implementation you use for the slash things is all configurable. So I really want to nail home that we make the runtime development very flexible for you, but you as a benchmarker kind of have to understand that this flexibility you have to benchmark it and you have to understand it. And one of the nice things about our benchmarking framework is that we benchmark against your real runtime. So we basically, as long as you're benchmarking it on your real runtime, you get all of the real implementations of these things. This just works for you out of the box. So it's what makes kind of our benchmarking framework so flexible for a million different blockchains, all using the same palette, all built in different ways. Okay, and then depositing events. And so depositing event, I want to point out, event is something that we assume is free in all the blockchains. So every single block there will be events being produced, and so reading and writing to events is something that was actually kind of free here. It's not saying that you should just do millions and millions of events in your blockchain. Like of course there is some overhead, and that'll be measured in the extrinsic time. Like there is some time it takes to actually deposit an event, but in terms of writing to the database, we don't count any event read or write. Okay, so now that we looked at the function, we kind of analyzed from my side, like, I'm a person looking to benchmark this runtime. I read the function first. I have an understanding of how it works. Now I want to go and write a benchmark. And this is what that benchmark looks like. I want to make sure that the screen updates. And if not, I'm going to restart my video. Yes, okay, it updated. So you can see here at the top, there's a kind of, okay, one, this is macro magic. So not everything in here is real Rust. And if you're still hung up on that, I'm really sorry. You're gonna have to wait for the Frame 2.0 release that Guillaume is hard at working on, which will be much better at showing you real Rust. But for now, we're doing macro magic, and so we have fun syntax like this at the beginning. So this at the beginning, this R, S, and X are the components of our benchmark. And they are basically those things I've been alluding to that can change over time. So we have a different number of registrars, sub-accounts, identity fields, all that kind of stuff. And so you'll see here that it's important that our runtime defines limits for all of these things. Otherwise, we wouldn't know how to benchmark it, right? And we make these limits configurable so that any different blockchain using this palette can define what they think is the right number of limits for their blockchain. So you can imagine that Polkadot has, like, say, a max of 10 registrars, but your blockchain, which may be smaller, only needs 2 registrars. Well, you shouldn't have to pay the costs of having more registrars if there's some kind of overhead caused by that. So you can see here that as a part of probably benchmarking this runtime, I would actually go through and introduce these new constants, these configurable constants, into the runtime configuration trait, and then take advantage of these constants in the benchmarking pipeline. And so it might be that you need to actually modify your own palette to be more benchmark friendly, if that makes any sense. And so yeah, we have here basically a definition of R, S, and X, and it will take values between 1 and the max value that is set in the runtime. And this fancy logic is basically how we're doing the for loop, right? We have a for loop here which says, like, okay, well, R at 1, and then S at max, and X is at max, and then R at 2, and then S at max, and X at max, and then we go through all the things, and then we start with S. So that table we're talking about is generated from here, so very simply written. And then within writing our runtime logic, we basically assume, okay, well, at any point in time, the R, S, and X have a value. So let's use these values to then do stuff. We're not doing stuff here, so we'll just look at the next slide. But this slide right here is just kind of showing you, okay, well, this is just like any test, right? Like when you're setting up an account that you need to use, you may need to, like, give it some funds. You need to maybe, generate the account from some seed or whatever. You do that all here just like you're running a test. Should be nothing new. You can take advantage of all these kind of background functionality, like make free balance be to give the user some balance and all that kind of stuff. So easy enough. You can see here's actually where we start using some of these variables. So you can see here, I have some internal functions like create identity info, and here's X. So here's the number of identity additional fields that we're going to give to this identity info here. So depending on what this value is, this function will generate an identity information with a variable number of fields. And then we set this identity to that user we created with this info, and then we can add a bunch of sub-accounts. We'll add as many sub-accounts as S's. So these are all just some, like, some utility functions we generate in our benchmark. It's not on the screen here, but you can imagine it just does some loops and basically sets things up such that the user account has all the assumptions we want to make about it, right? Okay, and then we add registrars. That's the R portion, right? So it's simple, just do a loop. And then finally, we actually make the call. So you can see here we use this successful origin, this special trait, to get the force origin here, and we actually even do kind of an assertion here. We assert that at the beginning of this function, the identity does exist, that it does contain a key, and then as simple as that, we actually dispatch the function and verify at the end that the identity does not exist anymore, which means we did successfully kill the identity and that our extrinsic measurement is correct. I will note here that this is actually kind of a more advanced way to call an extrinsic. So actually, I will note here something even more powerful about this benchmarking framework. Benchmarking framework does not just apply to extrinsics or dispatchables only. It actually applies to any arbitrary logic you want to run within your runtime environment. So the syntax here basically is putting a closure. So you could write any function you want here. You could write a for loop that just does print line. Or I guess print line you can't really do in the runtime. You could do something that just does a log here. Or you could do some kind of just hashing function here, whatever. Like, it doesn't have to actually be an extrinsic. It can just be a function. And we will be able to measure the time it takes of that function. Now there is a kind of a more friendly syntax, and I'll probably show it to you later, where it kind of assumes the shape of an extrinsic, so it just has the parameters just as you expect. But here you can even do things here like where we have a special origin, we need to use this origin to dispatch the call. Here I basically set up a call up here, and then I just call dispatch onto this call with the origin I want. And then it basically is executing my extrinsic. This is exactly kind of what we do in the background with the normal origins. It's because we have to use the special origin here, we have to write this logic. But you could imagine doing a bunch of things in here. I think one thing actually we talked about recently was encoding and decoding. If you were interested to see how long encoding and decoding takes, you could actually write in this code block, write, like some struct.encode, and you could actually measure how long that would take. And so it's really, really flexible what you can do inside this benchmarking, and especially if you want to take into account other parts of your process which may not be captured in your extrinsic, you can just wrap it all in this in the function here. Yeah, so any logic. Cool. So we have some ensure statements, all that kind of stuff. All good. So that's what the benchmark looks like. So executing the benchmark. So again, once you've written this benchmark, you compile it, you stick it into your node. There's some configuration that has to happen there, but then you compile your node using the feature flag runtime benchmarks, and then you get access to this benchmark CLI, and then you can execute the benchmark by basically giving it a bunch of flags. So you have the benchmark CLI here, the subcommand. I'm going to be benchmarking it on the chain dev, so you can actually choose which chain specification you want to start with to benchmark. You want to make sure in general to choose the chain specification that doesn't have state that you would otherwise not want. So I said that really poorly, but basically, if you introduce state into your chain spec, that state will exist when you run the benchmarks. So you as a benchmark writer generally are safe to assume that there is no state on the stuff that you're touching. But if for whatever reason, the runtime developer does stick some state in there, it may affect the benchmark. So, you can imagine like, what's a good example? Like the number of, or the validators on your chain spec, right? If you start with a chain spec where there's already some initial validators, and then you run a benchmark where you're trying to figure out, okay, how long does it take to compute the next validator set? Well, the validators in the chain spec will actually show up as a part of the benchmarking process for your benchmark. So in general, you want a chain spec which is pretty empty. Is there a question? I heard the mic go on for you, Dan.
Yeah, I just had it. Like, would you generally want to maintain a chain spec specifically for benchmarking, or is there any guidance around like which chain spec to use?
Yeah, actually, I think in general, having a benchmarking chain spec makes sense. I think like that, we haven't introduced it yet in Polkadot or Substrate because we haven't really needed to, but it totally makes sense, to do it. And this dev chain spec is actually, it's not defined as a JSON file. It's actually defined within the CLI. There's some stuff there. So it's very simple, for example, to write your own, basically, benchmark chain spec, which has no, initial configuration in it. So yeah, definitely that would make sense. But you might also be interested to benchmark your runtime with certain states. So we kind of give you the flexibility there. But using dev is, I think, pretty okay. You won't run into any problems, at least with our benchmarks. Okay, so we're always benchmarking with WASM. Of course, the runtime in the worst case runs in WASM. We actually execute with compiled. This is something that's a little bit interesting. The worst case scenario for running WASM actually isn't compiled. It's actually running it with WASMI. But I think we are pretty comfortable with compiled with the security of it, that we just recommend that all people running validator nodes would run their blockchain, making sure to run using the WASM time, the compiled WASM execution. And this gives us about a 10x improvement in speed. So I think in kind of the worst case scenarios, you have native, which is the fastest. It's 1-to-1. Then you have compiled WASM, which is about 10x slower, and then interpreted WASMI, which is about 100x slower from native. Or actually, I think it's 100x slower from compiled. Actually, it's one of those numbers. It's really slow. Anyway, this is one assumption we make that is not absolute worst case, but it's something that we tell our validators run with this configuration. And then, of course, you can select which pallet. Every pallet can have their own benchmark. You can select which extrinsic you want. You can actually even pass an asterisk here, and it'll run all the extrinsics. And this is the normal way we run benchmarks for a pallet. So we just run all the benchmarks for all of the extrinsics. But if you want to just run one, you can do that. How many steps you want to run? So this is, again, given a range given the range of your component, how many points do you want to measure? So if the component ranges from 0 to 100 and you have 50 steps, we'd be measuring every 2 from 0, 2, 4, 6, 8. What it would look like. So we get 50 different sample points for the components. And we'll do this across all the different components. Then how many repeats? So for every single set of components, how many times do we repeat that benchmark? Optionally, you can have some raw output if you want to actually look at the raw data of all the benchmark timings. And we've used this to kind of make some graphs. And of course, if you do this output flag, we'll output a Rust file for you with all the benchmark weights in it automatically. Cool. And then, of course, I have here another command you can run. So basically, you can also get logs from benchmarks. We have some very explicit database logs. So it tells you every single key which is being read and written to in a benchmark. And you can access these logs as long as you run in native. So these logs only appear when you run in native. As long as you do, we output these logs for you, and then you can also use that raw output to kind of analyze. Like if you're wondering, okay, well, my benchmark is saying that there's 6 reads, but I can only think of 5. Where's the 6th one coming from? You could take a look at the logs and figure out what that 6th read is, and then either fix a bug or basically take that into account. And so at the end of the process, so these graphs were actually generated using the raw data. But you can imagine in the background, our benchmarking process actually just does the same thing. But here are all the sample points. You can see that there's a bunch of different inputs here. We have a range of inputs. You can see there are outliers up here at the top of this stuff. And this is why it's important to take repeat samples, because we don't want outliers to really affect our stuff. And so we can take a look at the effect of the extrinsic number of registrars. It's a very, very slight upward curve, upward line. Here's the number of subaccounts, very clear linear pattern for the number of subaccounts. And then the number of additional fields looks basically flat to me. Could be a small overall increase, looks flat to me. And then also we have, you can generate graphs, and I use the raw database output to generate these graphs to show you the number of reads and writes for each of the components. Now, other components had constant DB operations, so here I'm only looking at subaccounts, but with the number of subaccounts, if you remember, there was this loop where we were removing subaccounts. You can see here that the number of subaccounts removed, or the number of writes, increases linearly with the number of subaccounts there are, exactly what you would expect. And actually here you can see that with 20 subaccounts, there are slightly more than 20 writes, because there are some other read and writes. But basically it's just exactly how many subaccounts there are increases the reads and writes, whereas the other database operations are constant. And so at the end of all of this, we have these line graphs, we have these database tables, all that kind of stuff, and we can generate for you automatically. This is what is generated in this Rust file, a weight function. And it basically does linear regression analysis and figures out exactly what the timing of your function will look like. And this, it took quite a while to actually get to this point, but this is, the epitome of optimism of automation here, where basically we ran everything for you and we give you a function. This is the base weight that for each a registrar, subaccount, or identity field, this is how much it will affect that kind of constant weight value. So there's some multiplication happening here. And then this is the base number of reads and writes. There are 3 reads and writes for base. And then, of course, there are 1 additional write for each subaccount. And it figured this all out for you automatically using linear regression analysis. And this is really cool. Okay. I'm going to take a pauser real quick, make sure if there's anything.
That all sounded pretty good to me, Sean. There might be a good time to go back in the question box and see if there's anything that feels right for you to answer now.
Yeah. So there's some show me how to, there's some questions about show me how to do X, and I will wait till I actually start programming, hopefully, to do that. And hopefully you're all interested to stay for a while, because I'm very happy to stay here for a while and just keep talking.
Oh, one note on that, Sean. I do think that Crowdcast cuts us off at 2 hours, I believe.
Okay. Well, that's probably a good cutoff anyway for me to stop talking.
Okay.
I don't see. Can you use benchmark to reverse engineer target block time? If so, how? That doesn't really make sense to me. If someone wanted to elaborate on that, that would be great. Yeah, target block time is something that you should define for your blockchain kind of based on the economics and principles of your blockchain. Like if you have a blockchain that is 1 second blocks, like you're already making assumptions about networking on your blockchain, how quickly things can propagate, etc. If you have like 60-second block times, that's also making assumptions about like kind of you value like a lot of compute over like really responsive interaction. So it's you shouldn't use benchmarking to define your target block time necessarily. You should kind of start with your target block time and then make and use pallets based off of that kind of limitations.
Can I take a second to see if like I can kind of help answer this question that Will asked at the beginning, or do you have a different plan?
How often should a substrate?
Oh no, I was talking about the why do we benchmark the runtime?
Oh yeah, sure. You can go ahead.
Yeah, so I'm not totally prepared to answer this question. So maybe there's like one follow-up question that I have. So we benchmark the runtime because we want to have a good understanding of how long things in the runtime will take to execute. And the reason that we do that is because this idea of block time is very important. We want to have a target block time. And so benchmarking the capabilities of our runtime, the features of our runtime, helps us ensure this target block time. And I think where my disconnect is that I somehow understand that this is related to the security of the chain, and that not having proper benchmarks will create an actual security risk. But my logic isn't quite connected there. So if you could kind of help close that loop.
It's about block producers. So at least in Babe and Aura and all that kind of other stuff, right? That I guess in Babe specifically, there are windows in which you as a block producer are allowed to produce a block. And this window there's a time limit, and this window is related to this block time. So within your time limit, you have time to produce a block, submit it to the chain, have it propagate, all that kind of stuff. And if you don't make your block in time, then you'll lose it. And you can imagine that if you create really heavy blocks and there are nodes who are the correct block producer for that block, for that window, but they weren't able to produce a block in time because they're still spending all this time importing their block, then the secondary block producer comes in. And they can take their slot. And let's say that even fails, then that block is missed, and then the next block producer comes in. And you can imagine this being like some kind of ability for you to DOS the network, and that all these block producers can't produce their blocks on time. And that, of course, itself has its own ramifications for security. But like this is the kind of the level of attack we're talking about here. That you are basically trolling your network with all these block producers because they're not able to do their job in the allocated time or window which we are giving them.
Right, and so Substrate enables you to cap the weight of a block. And so by doing these benchmarks, by assigning the weights correctly, we limit the ability of malicious actors to create unhealthily heavy blocks. Is that exactly the idea?
So that when you're importing a block and that block says it has a certain weight associated with it, and that weight again is it's verifiable because you can run the functions and then say that the weight matches what it says it is, right? Or you could stop importing a block as soon as the functions you run have passed the weight limit you would expect or whatever, like all these kinds of things, right? Once you get a block that says it has a certain weight, you can know that you can import it in a certain amount of time, right? Like a block that says it has weight 1 second or whatever, you'll import in 1 second, right? And so it's that. And then another thing is, there are a lot of services that depend on block time, right? Like when we talk about, like you being an exchange, right? Like how long does it take for n number of verifications or all that kind of stuff? Like there are a lot of processes where you expect the block time to be consistent. This is like kind of a almost like a user feature, right? So it's very important, I think, for a chain to maintain a consistent block time. Stuff like that. Yeah. Okay.
Yep, that's helpful. Thank you.
Cool. Okay, so then let's talk about weight integration. So once we've created this function generated by the benchmarking, we want to actually integrate it into our extrinsic so that it gets used. And so hopefully you're familiar in the past with this kind of weight annotation. And before, we were actually just pasting in numbers into here. Like straight up, we would have a number here. One of the things we've seen is that this isn't flexible. Is that what we do instead is that we can generate these benchmarks and actually have these functions be part of a trait, this weight info trait, and we can actually take advantage of this trait to basically give us the weight input. So we can see here there's a function kill identity, which is this weight function we had generated before. And into the input is the worst case scenario for this extrinsic, all of the max values. And then basically the weight of this function will be what you've configured or what you've measured the weight for it to be. That's it. And of course, that this initial weight will actually be a large overestimate. Like, it's very likely that your blockchain doesn't have the max number of registrars or the max number of sub-accounts or the max number of additional fields. So we can actually do, I probably have some things here for this. What we can do at the end is actually do a refund. This is the chunk at the bottom, where we actually refund at the end any weight we didn't use. So I guess that the key takeaway here is that, when you are trying to initially figure out the weight of a function, one of the rules is that you can't read storage, because reading storage is expensive. And so if it's expensive to even learn how expensive a function is, then it's a bad thing in general. Like if it takes a lot of computation to figure out how much computation something would take, like it is in itself like a bad weighting function. Weights have to be super streamlined, have to be basically just computation, just a small bit of logic. And so in order to get the initial weight of this function, we can't know how many registrars there are. We can't know how many sub-accounts this account user has. That would all have to read into storage. So we assume the worst case scenario. Then at the end, when we've actually killed the identity and we've read things, like we've read how many registrars there are, we've read how many sub-accounts this user has, we can then refund any weight which we didn't use. We can say, well, here's the real number of registrars, here's the real number of sub-accounts. And so there's kind of this interesting behavior where you have a function where it may be more like you have an account with 5 dots in it, and it may not let you call that function unless you have 5 dots. But the function at the end only costs you 1 dot of fees. What's happening here is that up front we're saying the worst case scenario, this function will cost 5 dots of compute. But at the very end, when you finish running this function, we see how that you only used 1 dot of compute. Like, when you're comparing weight to fee. And so we give you back the other 4 dots. And so this is kind of how we're able to achieve lean weight analysis and be able to kind of make it all work. Does that make sense? Okay. And we'll see this more later, but this is kind of an important piece of making sure that you keep your extrinsics safe while also making sure users don't overpay for extrinsics if they don't have to. Okay, so that was the overview. All right, I'm gonna jump into some of the things we tried and learned, and there's some learnings basically throughout the process. Like, we didn't get to this point just immediately. Like, we tried a bunch of things. Like, I spent more than 6 months toggling stuff and experimenting and learning a bunch of dumb stuff. So we're gonna talk about that. So the first was isolating database benchmarks. So initially, we wanted to actually use this black box and measure everything, including the database, all wrapped up in it. All wrapped up in as a part of benchmarks. We were actually going to populate the entire chain state with what we expect there to be a large number of items. We were actually going to run the benchmark, actually have it write to the database, all that kind of stuff. First, this was super slow. Like, populating a database and the Merkle tree, all that kind of stuff, doing it thousands of times for the number of repetitions is super, super slow. But even worse than that, actually, was that it wasn't even consistent. If you look at this graph here, this is a real graph from our process. And I was banging my head on, like, what the heck are these outliers? Like, you can see here, there's a pretty flat curve. And you can actually see here that it's probably not flat when you go close, but these spikes are on the order of 1,000 milliseconds. So 1 second, 2 second spikes, right? On a function that's probably on the order of microseconds, right? So I'm seeing here that there are consistent spikes in these benchmarks at random intervals that cause 1 second delays, and there's no way you can do accurate benchmarking here. And we figured out this was really RocksDB, and this is RocksDB doing some crazy magic. So in terms of what we learned is that RocksDB is crazy. We're definitely working on things like ParityDB. Hopefully that will be a good replacement and may have more consistency. But we have to isolate, we have to remove the database kind of component out of the benchmarking system and instead use it in memory DB. In-memory DB is very consistent, very reliable, very understandable, and basically measure database kind of from an external standpoint. So the way we measure the database reads and writes, as we saw here, we count the number of reads and writes, and then we actually do separately a whole suite of benchmarks around the database operations and how long it would take on average to do a read or a write to the database, given some assumption about how big that database is. So this actually, that benchmarking is not part of my runtime benchmarks or part of this presentation. It's actually part of the node benchmarks. But that's for another time. But anyway, this is something we learned. Another thing we learned is that we found some non-linearity. So we talked about the kind of, it's very important that the runtime behaves linearly. But we found in our own implementations that there were things like events, and that the number of events in your, or the number of transactions in our block was causing a non-linear increase in the block time. So you can see here that there were 500 transactions. It was 200 milliseconds. 1,000 transactions. Oh yeah, okay, I think it just caught up. 1,000 transactions is 500 milliseconds. 2,000 transactions is 1,400 milliseconds. You can see here that we're definitely non-linear in the number of transactions. This is bad. It should be that the number of transactions is we include is linear to the amount of time it takes to execute that block. And what we found was that actually the problem here was to do with events. That events in Substrate is a vector. And as you submit more events, we just add, we append new items to this vector. What we were doing kind of naively with this API was that every single time we were adding an event to this vector, we were actually passing the whole event object over the WASM barrier. So basically, it was this object that was growing was also getting passed bigger and bigger and bigger back and forth between runtime, add the event, push it to our memory, and then read it again, push it another event, push it memory. So it's getting bigger and bigger. So instead, we updated the API. Actually, this is an improvement to the overall append API across all people using storage, that now it's when we append, we only push the new item across the WASM barrier, and then of course we append that item on the native side. So that's an improvement here. You saw here actually that before, without this improvement, the import of blocks was 17 seconds, and after, the import of the block was 700 milliseconds. So we have a 95% increase, like from 20 seconds to 1 second, basically. This one change we found improved in terms of block import time. So super cool. We learned this and we fixed it. Also, you notice I have PRs here. So if you want to look at what PR and kind of look at the code, you can absolutely do that. Weight refunds. We already talked about weight refunds, kind of giving you back your weight, but we saw in general that the worst case scenario weight is very much not the average weight. And so if we charged everyone the worst case scenario weight, we would have a really expensive blockchain. And we have a blockchain where it wouldn't fit many transactions, or you'd have to change basically how you write your functions. And so by having this weight refund, we basically can ensure that when we give users back the funds that they should have, and that we can also say to the blockchain, hey, we thought this extrinsic would take 1 second, but it only took a half a second. So you now have an extra half a second to fit other extrinsics in there. So this is an important PR that we got. And then, of course, we have customizable wet info. So as I mentioned, the original benchmarking weights looked like this, where we basically had a hard-coded number, and we had this DB weight stuff. We already had DB weights at that time. We basically had these hard-coded numbers. And this was really not flexible. Basically, we made an assumption that everyone was running their blockchain like we ran it on Polkadot. And if you didn't, well, it sucks for you. And that's not a really great attitude for an open blockchain framework, of course. And so what we had to do was basically extract out all of these weight formulas into these traits, and then allow you to configure these traits just like you configure other parts of your runtime. And so by extracting these weight formulas into this weight info trait type, basically, and allowing the benchmarks to generate this type for you, every single person can have their own version of this formula. If you wanted to, you could create a unsafe blockchain where the weight of everything is 0. And that's definitely up to you to decide. But the better idea is that every single blockchain has their own implementation and can take into account their implementation details by using this configuration trait. And we actually found that this solved a lot of the problems we were running into in terms of benchmarking, in terms of basically, like, we were trying to scratch our head on how are we going to handle these abstract traits, like what happens when someone uses one of our pallets but uses a different balance module. Like, we were gonna basically like, oh fuck, everything is messed up, like we had no idea what to do. But now that we allow users to basically benchmark their real runtime and then configure their own weight formula, we basically solved this problem. We solved all of the configuration issues by just making this formula configurable. Now, I think that there's still improvement to be had here. I think one of the things that we're missing is that the the signature of this weight info function isn't flexible in itself. So having a weight formula, for example, let's look at transfer. So transfer here is a constant time function. So we're saying that a transfer doesn't matter how much you transfer, doesn't matter who you transfer to or where you're transferring from. A transfer is always constant. That makes sense for a normal blockchain. Imagine you build a crazy blockchain with some crazy rule which says that, when you transfer a lot more money, do all this crazy computation. And if you transfer from me to you, do some other crazy, I don't know, you imagine some stuff where you may actually want a transfer definition that has some other variables in it. Right now, we don't have the flexibility. I don't know if we can enable that or not, but that is something that I would be looking to improve, to really have as much flexibility as possible, like where you can even define your own inputs here. Now, how that works with benchmarking and all that stuff, I'm not exactly sure, but there's always room for improvement in terms of flexibility. But this is already a great step forward in terms of customizable weight info. Yeah, so those are some of the things we've learned and kind of how to get to where we got. And now I want to talk about some of the best practices and common patterns. So given what we learned, given what I've shown you, there are some patterns here where certainly you'll run into them. So let me just tell you what we've kind of decided internally as the best practices. So best practice, we've already kind of touched this a little bit, but initial weight calculation must be lightweight. So I kind of mentioned this already, that storage operations are quite expensive. You cannot, in your weight calculation, look into storage to figure out how expensive the function should be. If you did this, basically you'd be introducing on the order of the extrinsic time that much magnitude of additional weight to your function, and this is not good. And this is again, it's a rule that can be broken. Like you can choose not to follow this best practice. Like it's no one's stopping you here, but in general you should avoid it. And so how do we get around this in Substrate? Well, we basically add bounds. We add bounds and assume worst case. So we basically all the time and all over the place. You might notice this if you've been playing with Substrate. We have these different configurable types and traits, which are like the max number of users, or max number of locks, or max number of XYZ. These things are basically allowing us to give reasonable weights to these different extrinsics by assuming what the worst case scenario could be. And so if the worst case scenario is that there's a maximum of 50 locks on a user, we don't need to read into storage to know how many locks there will be on a user. We can just say it's 50 locks. And then at the end, when we actually manipulate the locks and we can see how many locks there are, we can then refund that weight. So this is a common pattern that we use to solve this problem. Now, again, you can, if someone were to say, what about this situation where I would want to read from storage? Like, I bet you could invent a situation where it would make sense to read from storage, but it is important that you know the best practice and you know the common pattern to solve it. Okay, separate benchmarks per logical path. So, functions can be complex, and functions can have multiple different execution paths. Like, if it's if the user is part of group A, do this. If user is part of group B, do this. And so the general best practice is to basically create benchmarks which tackles each of the individual scenarios. You may not know which scenario is the most expensive one, so you benchmark all of them. And then, as a common pattern, you may use these different weight info benchmarks to basically, and some kind of comparison operators to determine what the weight of the function should be. So, it could be, I'm trying to think about some exact scenario, but basically you see here, we have 3 different paths, and we say, okay, well, the weight of this function is the maximum of these 3 paths. So let me give a kind of contrived example. And let's imagine that part of these weight info formulas is the database operations. Imagine that I have a blockchain where the extrinsic time is bigger than the database read-write time, just by nature of which database I've chosen and what CPU I want to use, right? It could be in this situation that path A is the most expensive for my blockchain. Let's say that you have a blockchain which flips it, where your processor is a different assumption, it's much slower, but your database is much faster. So then it makes it so that the balance between database operation and extrinsic operation is changed, which means that possibly path B is now actually the more expensive path in your blockchain. So it may not be clear which path is most expensive based off of the assumptions we make about our blockchain or anything like that. So you as kind of a runtime developer, just benchmark all the paths and then just having the weight formula, just picking which one is the most expensive, right? And that's a common pattern to solve this problem. Another thing in general, as a thing, is you want to keep extrinsics simple. So, creating extrinsics with have multiple paths is sometimes unavoidable, but it is sometimes avoidable. So sometimes you can just make extrinsics have kind of fixed functionality. And whereas you have one function which can do two things, have two functions which can do one thing. And basically, the more simple you can keep your extrinsic, in general, the more accurately you can measure the weight of that function. Because you don't have to make so many assumptions about the worst case scenario. You just keep it simple so that the extrinsic that you have is just easier to have. And then using the pattern is then take advantage of UI and things like batch to basically combine that logic. So I'll give you an example here, like vote and close vote. So in our democracy systems, voting is very cheap. Let's see that the vote, you need 5 out of 10 people to vote for something to pass. The voting 1, 2, 3, and 4 is very cheap. It's just marking yes, this person voted. When you get to vote 5 and you want to actually execute that vote, the actual ramification of everyone passing the vote, it could be a runtime upgrade. It could be something crazy expensive, right? So if we had combined these two things together to make it slightly easier on the user, we say, okay, well, when the 5th vote comes in, we'll execute automatically. Well, basically, we don't know which vote extrinsic is the 5th vote, right? So we have to assume every vote coming in could potentially launch a runtime upgrade, and that's crazy. It would cost literally hundreds of dollars to even make a vote. We may not charge that because we can give you a refund, but you would need to pay up front how much the worst case scenario could be. The better solution is to have a vote extrinsic, which all it does is tally votes, and then a close vote extrinsic, which checks, hey, can we close the vote? And if so, close it. And the close vote extrinsic will assume the worst case scenario, that the vote will close and the thing will execute. And basically, for you as a UI person, basically you can just still get this nice user interface by measuring in the UI by knowing when the vote would close and then batching vote plus close vote together as a single call. And the overhead of batch is like basically nothing. So whereas you might want to write these very nice UI-friendly extrinsics, I would say definitely go towards simplicity and take advantage of these downstream calls or these downstream kind of logic to basically batch and take advantage of like the friendliness. And I think this is actually not only coming up with weights, but a lot of people often ask, why can't we just make things simpler? Why can't we just have payouts to stakers automatically? Why can't we just have more payouts? All of these, I talk about payouts, but all of this different awesome UI functionality. And I will tell you this, that user interact with the blockchain is very important, but it is not the purpose of the runtime to be a user-friendly thing. The runtime should be a state machine. It should only accept the minimum amount of information it needs to execute what it needs to do and what it needs to do correctly. And that you should use further abstractions, which are much more lightweight, to do all this additional overhead. Because if you introduce overhead to your runtime logic, if you have a network of 1,000 nodes, all 1,000 nodes absorb that overhead. But if you have a front end which does the overhead, only the user interacting with that front end uses that overhead, right? It's much better, and you don't have the assumptions when you use a front end about the runtime environment, WASM, single threaded computation, all this kind of stuff. Like it's just so much better to keep your extrinsics simple and to split them out and all that kind of stuff. So this is something that I cannot emphasize enough. Like I think that I could have a whole day conversation about all the decisions I would make about different extrinsics and how you would design them based off of this kind of principle of keeping them simple and keeping them kind of focused on the plan goal. I hear you unmuted. Is it something
I'm just unmuting because it's the kind of thing that I couldn't talk enough about either. Like it's basically just like what you're talking about now is good software design. Like you keep things modular, focused, simple. I dropped my little 2 cents here in the troll box that people are terrible at evaluating even moderately complex systems. And so, yeah, I just agree with everything that you're saying. And it's really important to remember that when you are developing Substrate runtimes, it's much, much different than developing a Node.js application or something like that. And it's much, much, much more akin to systems programming. And
it
so
is system programming.
It is systems programming. Exactly. So you don't think in terms of cramming everything into your system. You think in terms of composing the fundamental capabilities of your system into friendly workflows. But the system itself must remain simple.
Exactly. Yeah. Okay, and then minimize usage of on-finalize. So one of the best practices is to not use on-finalize when you don't need to. So I kind of have a graph here. So basically, on-finalize is a chunk of logic and execution which must execute. Like, it's not like an optional execution. Like, in order, your blockchain, if you have an on-finalize statement, it must execute, and it executes at the very end of the block. So you can imagine, in general, it's that on-finalize is kind of a hard piece of logic to fit into the weight calculation, because if the on-finalize weight is variable, and you're trying to fit in as many as extrinsics you can, all that kind of stuff, and the amount of time it takes for on-finalize doesn't quite fit what's available left in your block execution time, then you risk basically running into blocks that are overweight. And it can happen occasionally. I mean, sure, that whatever, but in general, like, avoiding the use of on-finalize, instead, like, moving logic to things like on-initialize would be much better. And so the common pattern is basically to transition logic in general to on-initialize. So things that you might want to do at the end of a block, maybe you can do at the beginning of a block, right? And there are some things which you can't do, you can't help but put at the end of a block. And a common usage of on-finalize in our runtime is basically cleaning up transient storage items. So I'll give you an example of what is a good example? An example is something like the timestamp. So in timestamp, the timestamp itself is stored into the chain, but there is this transient storage that we have, which is like, has the timestamp been updated? And so this on initialize, we update the timestamp. We change this, has timestamp been updated to true. And then the on finalize, we basically check that yes, this was true, and then we delete the storage, so that we don't actually ever push this value into our Merkle tree. We just create it and clean it up. It's all transient. So this is something that we can only do in on finalize, but this is okay. It's something that it's constant time. It's totally lightweight, no problem. But there are other things like doing the payouts for all the validators. Like, you might want to say, okay, I want to do all the payouts at the end of the era. What we would say instead is do all the payouts at the beginning of the next era, or do all the payouts at the beginning of the block of the last block of the era. Something like that, right? So these are the kinds of things where something variable, where you have to do all these payouts. Doing it in an on finalize would be very difficult to accurately measure the weight. But if you are able to measure that weight, you need to stick that weight into the on-initialized block. So if you actually look at the function definition, the function signature of on-initialize, the on-initialize function returns a weight. The on-finalize function does not. So on-initialize is responsible for returning any weight of the on-finalize, or you're responsible for wrapping any on-finalized weight into the extrinsic, which may cause some additional on-finalized weight. So you can imagine that if 10 people call this extrinsic, there'll be 10 instances of some kind of on-finalized logic. So you're responsible for wrapping that weight of the on-finalize into the base extrinsic, so that it's at least accounted for before on-finalize gets there, right? So when you get to the point of actually executing on-finalize, we should have already taken into account the weight it's going to take. Cool. And then, of course, the limitation of pallet hooks. So we talked about this already. I don't think I'm going to go over it again, but basically pallet hooks are very flexible, they're very powerful, but it's easy to fuck up. So just in general, keep hooks constant time. In general, if you have some assumptions about what you're able to benchmark or do, you must make those assumptions up front, and it's a kind of understanding between the pallet developer and the runtime engineer. And yeah, and then what's next? So benchmarking actually has gotten really, really far. I think it's to the point where all the hard stuff is actually pretty much done. And what we really need to do is basically improve a lot of the user friendliness, improve a lot of the making it automated and making it work for your situation. So like, I'm still working on making it fully automated for Substrate and Polkadot, but everyone's blockchain, their CI tools, how their weights in runtime is set up, it might be different. So what I would hope is that we're going to get some external contributors looking to basically improve the user friendliness of this whole pipeline. And I think it's definitely very approachable. especially if you're not familiar with Substrate, but you are familiar with Rust. So this is something that would be very good. But there are some bullet points here on things that we might want to improve on and contribute in the future. And so I will jump into questions, but I have some time to also kind of go into the code and maybe do some kind of benchmarking or something. I don't know. We can kind of do whatever at that point. But that was my my talk. And
I definitely want to make sure that we get the questions answered.
Yeah, for sure.
So I'll let you kind of prioritize how to answer them.
Yeah, I'll just start with the votes. At this point, I've talked about everything I want to talk about, so anything else will just go. So the first question I see from Will is, how often should Substrate Builder change their weights? It seems as though these weights have changed a lot, for example, on Polkadot for the past few months. Is this because they were being fine-tuned and weren't efficient at first, or because of the necessity of the code changing a lot? So basically, you need to update your weights anytime your runtime changes. So every single runtime upgrade, we do new weights for our runtime. Additionally, we haven't really quite done this yet for Polkadot, but at some point when the Rust compiler stabilizes, or when we want to basically stabilize the environment, like we want to keep Rust dependencies, like the Rust compiler we use, the nightly version we use, what exact crate versions we're using, all of that constant, because that also may affect the weight. Right now, we're basically, kind of updating these compiler stuff kind of on the fly, and we're just doing, benchmarks, every time we update the runtime. But you as a runtime developer should be updating your weights whenever you make a change to your runtime or something that could affect the speed of your runtime execution. And then, yeah, they get tuned a lot because, of course, we were fine-tuning the weight process, and also because, we've been pushing a lot of updates to Polkadot. Polkadot itself has gone through a bunch of runtime upgrades, and each time we want to update the weights of the pallets that are affected. It may not need to be that you reweigh all of the extrinsics every single time. You may only need to update the weights for the extrinsics of the pallets that you touch. But if all this is automated, having a one-day process kind of just run all the benchmarks is probably not a bad idea for a production chain.
And when we're talking about weights or hooks, if you update the balances palette and then like 15 of your other pallets hook into that balances palette.
Exactly. Yes.
Yeah.
That is exactly right. You need to be conscious of the fact that updates to balances palette also affect all the other pallets downstream. That's perfect. Okay, so isn't it better to make the concept of weight arbitrary and dynamic, like Monero with block size limit, that changes over time and automatically when needed, compared to empirical and fixed? So, for example, in the former, we allow an arbitrary initial conservative reference weight, and then we study how that affects the nodes. Over time, if we're hitting the limit of the weight, we increase it by a couple percent. With the fixed weight I see here, it seems that we have a lot of prediction we have to do in a complex system. So yeah, I think Joshi touches on this a little bit. But basically, yeah, so we can say this is that in your blockchain configuration, you get to define what the max block weight is for your blockchain. So if over time you want to change this so that your block, the amount of stuff you can execute in a block window goes from 2 seconds to 3 seconds, you can change your block weight limit, or decrease whatever. You can change that block weight limit, and all the weights will still fit in correctly. Now, I think what you want to do here instead is like just trying to say that, okay, well, what if we just kept all the weights the same, and instead of tweaking the weights every time, we just tweak the block weight number? I think that's what you're trying to say, Sam, right? And if you're still here, let me know that this is on point. So basically, instead of redoing all the weights and saying, okay, well, all the weights are 10% more expensive or cheaper or whatever, let me just put on the quick slides, that we can just increase this block weight limit so that it's either 10% bigger or smaller, something like that, right? But this is not really super efficient for a few different ways. One is that knowing how much this weight changes itself would require some kind of benchmarking, right? Like it would require some benchmarking of how big or small this thing gets. And then you're saying automatically, but I don't know what automatically means, because you need to run a benchmark to know how long it takes. Like you might be thinking like, okay, you want like all the nodes to report how long it took them to import the block and then adjust based on that, but you don't know if all the nodes are running your base hardware. And then if you don't know all your nodes are running the base hardware, and let's say the weight changes, you don't know. You're saying about like proof of work here, like basically like the how complex or difficult the hashing algorithm is, right? And it just doesn't work in this way, because the complexity of fitting extrinsics into our blocks is like much different. And really, when it comes to proof of work stuff, the largest overhead of the proof of work time is not doing the extrinsic transactions. It's doing the proof of work calculation itself. And then even like Ethereum, so I see you're responding to me, but in terms of things like Monero and Bitcoin, for example, like these classic proof of work chains, they don't have arbitrary logic. They just do transfers. Look at something like Ethereum. Ethereum is a proof of work chain, but they have this concept of gas limit, right? And this gas limit is a fixed number. So exactly like we have a weight limit, they have a gas limit. So in terms of computational proof of work chains, what you're describing is actually not the de facto way. If you're talking about a transaction-only chain, you can make much easier assumptions about what the weight system is, because you're not doing arbitrary calculations. You don't have arbitrary pallets. If you're only doing transfers. In the case of here, we have this open blockchain framework where you can basically build any logic. You have a logic to do this complex calculations. You need to address the problem differently. And so when we look at things like Ethereum, which is a proof of work chain, we have a one-to-one mapping of ideas here. So I don't agree with your assessment. And again, I think in terms of flexibility, this is just a much better approach. You just having weight be constant to time makes people understand when they're configuring the runtime. I have my maximum block weight being 2 seconds. Like this is a sensible logic. You don't have it be okay. It is something changes. Ethereum gas limit is it increased over time, but it increased using council voting. And one thing you will notice is that Ethereum gas limit is changing, but the gas prices themselves don't often change. And this is kind of because I think they don't really have as clear of a dynamic benchmarking framework as we do. Like, I don't know like what you're looking to achieve in terms of one implementation or the other. Like you could implement the other way. I really confidently believe that our implementation is the more flexible way and the more kind of correct approach to the problem, because Ethereum is just one blockchain. Our platform, Substrate, our pallets are for many different blockchains. How can you talk about the weight of a pallet adjusting for 2 different blockchains very easily? It's not. It makes sense to benchmark things at the extrinsic level and to have it be done at the blockchain level dynamically at that point. That is my perspective, but maybe we can take
Sam, or we could bring Sam on screen. That I want to be like the devil's advocate and throw that idea in there. Sam, if you'd like to come on screen and chat with Sean about this, just let us know and we can do that.
Yeah, maybe let me get to the other questions first. And if you have time, then that would make sense. Okay, so is there significant difference between x64, 64 on performance? I have no idea about the difference between the performance of these different architectures. You could do a test, but I think, I assume that our WASM has certain assumptions about the stuff. So I don't think at the level of the ARM architectures you will get performance differences. It's like we're actually running in a WASM environment. So I don't know. I'm not the right person to answer this question. I'm sorry, but you can do benchmarking to figure it out. So that would be something that if you'd want to try and tell us, like that'd be awesome. Can you please show us how to initiate the state in a benchmark with using pallets that don't in dependencies of benchmark pallets? Right. So okay. So I think you're trying to ask here. You want to initialize a state of something in your benchmark, but it's not in your pallet. It's in someone else's pallet, right? And so this is where you have to take advantage of hooks. So a common example actually came from this example I showed with the identity, where we had to populate the balance of a user. So in general, you shouldn't be writing benchmarks. Here, let me make this big screen. You shouldn't be writing benchmarks. You shouldn't be writing pallets which have hard dependencies on other pallets. Well, okay, you shouldn't is a strong word. When you make a pallet have a hard dependency on another pallet, basically you're forcing every user who wants to use your pallet to use these things coupled together. That might be okay for your blockchain, but I think we encourage that pallets should be flexible and open, such that any user can go and pick up a pallet that you've developed and add it to their blockchain. This is like how we're going to encourage a rich ecosystem of blockchains built on Substrate, right? So this is the pattern that we follow when we do our blockchains. And so when I'm benchmarking identity, I don't make an assumption about which balance pallet I use or which other pallets are there. Instead, I have to take advantage of these traits. And so I know that there's a balance I need to set here, but I don't know what that storage looks like. I don't know which pallet is being used as my balance pallet. So I will, in my benchmarking, I will basically use the currency trait to make free balance B. And this is basically a backdoor to a storage write, which writes into storage what the balance of this user is. So when you're designing your pallets, you should make sure as much as possible to be able to basically use these generic traits and these generic functions to populate the other storage. Now, every once in a while, I bet you will run into problems where maybe the developer didn't really think about the situation and you need to change storage. You could write benchmarks in their own crate. And when you create a benchmark in its own crate, and we've actually done this before in Substrate, so I'll show you a few examples. Make my screen a little bit bigger. So an example is, I think is in Grandpa. Nope. It's in one of the consensus ones. Like I'm online. Nope.
Sean, would this also be a case where you could use the chain spec and set the genesis state?
Yeah, I mean, yeah, you could for sure. That is definitely another approach. It's a little bit more hacky, and I imagine that if you want to set storage for a benchmark, you might want to specifically control what that storage is for different situations. I would say the more general approach would be here. So the normal way we have benchmarks is we actually have a benchmark file, which is just a module inside of the pallet crate itself. But you can see here in this offenses benchmark, we actually have a separate crate for benchmarking. It's a brand new crate. And the reason we do this is because in this crate, we can actually import not only offenses, but import a bunch of other pallets, which we assume exist. So right now, our offenses benchmarking doesn't work for any situation which doesn't have all of these pallets. And so our benchmarking for offenses is not generic. But once you've made this assumption that all these pallets exist, you can basically let me make this smaller because you don't need to see all this crap. You can basically make an assumption like this. You can see here that that my benchmarking world must satisfy all of these traits. And so when I'm importing this benchmark into a runtime, the benchmark crate itself will not import into my runtime unless it has all of these crates in there. So we're just using basic matching of like does your runtime satisfy the traits I require, and then at that point we can actually go ahead and call into the individual storage items of all of these crates themselves. I don't know if there's an easy example here. But yeah, like so here's the offenses, but here we're calling into a function from staking. So unfortunately, staking doesn't, I guess, open the right APIs to make it flexible. But you can basically make this crate in a benchmarking world where it has all of the assumptions baked into it, and then you can benchmark your runtime. This is definitely not the average scenario, but you may come into it once in a while. And usually, this implies that you should open an issue against a pallet developer saying, "Hey, you did not make your API flexible enough. Give me some more hooks." Okay. Right. How much can a block production and import differ? Is this a problem? Because you mentioned that weight is meant to be indicate block import. DOSing will be on block producers, right? So so block production versus block import. So the reason, again, we don't care about the time for exactly measuring block production time, and there are slightly different overheads for block production time. It should be about the same as block import. So block production, block import is very similar, but there are some overheads, like you're like fetching from the transaction queue, I'm sure, and then trying to do some fitting and stuff. But we don't care about this because we know that different nodes will have different hardware, and I guess what I would say is it's on them at that point. If they want to be a good block producer, it's on them to either improve their hardware situation, improve whatever, to make sure that they're producing blocks on time, which match our weight situation. What is not fair is that for all nodes, independent of what they're doing, have to import blocks. It's not fair to them to have that part of the process be overweight or not fit in the time. So that's why we care about that process the most in terms of kind of being a benchmark of how long this whole process should take. And so, again, that block import and block production really doesn't differ that much. I think that we do have some benchmarks which show the difference between the two. But in terms of what our benchmarking times are trying to target towards is about this block import time. Okay. Yeah, and then you create, like, and I'll give you an example. If you wanted to maliciously create an overweight block, you're really only hurting yourself because you spent extra time producing that block, and then other people won't import that block because either the weight information is wrong or the weight value you stuck into the block doesn't match the consensus of which, when you actually execute the block, like, you will have a discrepancy in what the actual values would be, right? Okay. And then, so there's a question from Thomas so the pallet will be deployed to the relay chain. And I'm sure this was a question from when I was talking. So the pallet will be deployed to the relay chain. Oh, so this is probably a question related to how weights work with parachains. And to be honest, I think maybe I've been talking for a while, but my brain isn't functioning. But I really think what will happen is that parachains will have to follow the same restrictions of the Polkadot relay chain. But in terms of the benchmarking, you'll notice that all of this benchmarking pipeline actually is also in the runtime. And so we only generate this pipeline when you compile your when you compile your node or compile your runtime, basically, with this features runtime benchmark. This runtime that's generated is not good for production. This is it is a bloat-filled runtime. It has a bunch of extra code in it for benchmarking. So in general, when you build your node, you don't include this feature flag. You shouldn't need to. But when you're specifically running benchmarks, you run with this feature flag, and it builds in all this extra bloat into your node binary and into your runtime, which then does the benchmarking pipeline. So none of this benchmarking will get deployed to the chain. And anything you put behind this feature flag will not get compiled into your runtime. So all of this benchmarking stuff, it's really important to isolate that functionality from your WASM to avoid bloat. Okay, any more questions? We're almost at 2 hours.
We're at 2 hours. I asked Spencer if he still had a question because I know that he had asked something in seminar. I'm going to see if Sam wants to come online because I think that would be kind of fun since he said that he would be into that. So I'm going to invite him on screen here.
And if for whatever reason we can get Crowdcast to last a little bit longer, I would love to, grab a random palette and maybe add some benchmarks to it real quick, or at least give you an idea of the looks. I mean, I hopefully in my presentation, I really actually walk through exactly what I would do in person anyway. I would just look at the extrinsic, understand kind of the components of it, understand the different ways that it could be affected in weights, and then I would benchmark it. But yeah, hey, I see Sam is here.
How's it going, Sam?
Hello. Hi, guys. Thank you.
So did you have some more questions for Sean?
Yeah, it's just my concern is that the weight functionality is something very relative and will change over time. I bet in 10 years things will be different and the blockchain throughput should be different. So on one hand, we have chains that will only do value transfer. Let's assume something like privacy layer that will be done on Substrate. They do not care about weight in any way, shape, or form. They should not. On the other hand, we have other blockchains that are complex, like Moonbeam or Edgeware. Those need to do measurements for the weight per block, but they do not have to make it also as measured in computational time. What they could do is they could have something reference, like I discussed before. But what I wanted to add there is that we can always start with something we don't know, and then the benchmarking can be done only in the development phase. My problem with weights is that it adds the benchmarking or the measurement to runtime, and it could be completely unpredictable doing that. So why don't we just go with bounds? We bound things simply by running them in the network and see how they act. And then if they require more or less, we can adjust to that, and then we will have a stable state that can change over time. It's just like the idea of proof of work. I'm quite sure you got that. But I was hoping that would go also for weights, because this benchmark stuff is extremely complex, as we all saw. So that's basically my concern.
So I will say a few things. So one, that our approach to benchmarking is opinionated. And even our approach to developing Pallets is opinionated. Like, you don't need to use Frame. You don't need to use our benchmarking platform. Like, you could absolutely design other pieces. Substrate is flexible at that point. For our needs and for what we envision Polkadot and the other Polkadot parachains and other substrates be, we think this is a pretty flexible platform. But kind of speaking towards this kind of trying to figure out what the weight should be. Again, you're pointing to things like Monero and Bitcoin, which again, my argument is that these are transaction-based chains where the majority of the time spent building a block is not executing the transactions. It's very low logic to do transfers. The time spent is actually just doing the proof of work. And the adjustment mechanism there is to adjust how complex the requirements are for the final output of the proof of work to match a certain block time, right? And so this kind of system, you can have. I think it's reasonable to make this kind of assumption where the block time adjusts over time. But I will say this too, that even these kinds of blockchain systems have felt security issues due to these block timing things. I'll give you an example. A 51% attack is often done because one chain assumes a certain complexity, a certain difficulty about the blocks being produced. And then a private chain will then take much more computational power, take advantage of the consensus of what the block difficulty should be, produce many, many times more blocks, a much longer chain than the other one, and then say this is the canonical chain. So when we talk about security, what you're saying to me is this kind of this self-discovering weight mechanism is actually not very secure. There's an attack right there built into it. And our mechanism doesn't have such an attack because we make upfront an assumption about what the hardware we require to be. If our blockchain has an assumption which is well, I guess we don't have proof of work, so there's not really an attack on who is the block producer. We have Babe, which assigns block producers. But imagine we had a proof of work system where our proof of work computer assumes a computer much lower in power than the one that's available out there. Your chain will be attacked. So our weight system assumes kind of a baseline of what the assumptions are for your network, and again, I think that your idea to do self adjustments doesn't quite fit into these systems, especially in terms of security. And finally, I want to say that again, I would challenge you to really look at Ethereum. I think we can both agree that Ethereum is a proof of work blockchain. Ethereum definitely has a difficulty adjustment mechanism, but if you look at the contract execution, it's my understanding that the gas limit is not something that adjusts block to block. Gas limit is something that you have to adjust through a Ethereum referendum or Ethereum improvement proposal. So you need to push an update to the whole network saying what the gas limit for a block will be. And this is exactly the same as kind of what our model for weight limit and weight per extrinsic.
Actually.
Yeah. So go ahead.
The part where the gas was because it was changed. I'm not sure whether it was changed with a referendum or it was automatically changed. But I can see hard limits created problems in Bitcoin, and I hope they will not do in any Substrate application. And given that Substrate is extremely dynamic, there are going to be all kinds of applications, and some of them will not even care about weight, and some of them will. So
yeah,
I don't know.
Okay, so I think that what you said is absolutely true. That there is a blockchain that. So again, the fundamental thing I started with was that there's that we assume some target block time, and we're trying to keep things safe for that block time. I think what you're saying is that there will exist chains who do not care about the target block time. They just want to produce the block. I would agree with that there are chains like that. I would think that our pallets are not well suited for that kind of blockchain. I think that kind of blockchain would need to make different assumptions about like Frame, for example. So like Frame would not be a good basis for that kind of blockchain.
I'm sorry, I did not exactly mean that they will have like an arbitrary block time. What I meant is that they will not care because no matter what they do, as long it will be streamlined and very smooth, that it will never go above 1 second. They don't care. So like if you're doing something like a privacy coin or something, you're not going to have contracts. So if all you have is transactions and transfer, you can easily scale linearly. you can imagine that every extrinsic is going to be the same. So you don't care about weights at all.
Yeah, I think that I think that you, in that situation, for example, you could forego all of the benchmarking I have here, and you could basically create a new, like, assuming you want to hack something like what you described onto my system. And let's say that you make a block sheet that says, I support 1,000 transactions. I don't care what they are. I just support 1,000 of them, right? You could basically have the exact have a weight, a maximum block weight of 1,000, and have the weight formula for every single extrinsic be 1, right? And so every single extrinsic will have block weight 1, and it would just work. There's no benchmarking pipeline needed. You know, based off of your own experience, that all of these extrinsics fit below this threshold. I think that this is something that's doable, but I think that this is not.
Can we dynamically scale that 1,000? That's basically my concern.
You could, yeah, you could. The block, you would have to slightly tweak our frame system. Our frame system, like, you would have to basically, instead of having it be configurable and hard coded, you would store it into storage, and then you would adjust storage, and then you would use that as limit for block weights. Our frame system, which does have an opinion on this, would not work out of the box for what you want to do. But if you were to fork Substrate, I think that you could achieve that within 5 hours of coding.
Okay, gotcha. Yeah.
Yeah.
As long as it's possible, then we're cool.
Yeah. Yeah. But I think, I would hope, and this is something that would be great, to get feedback from other blockchains building. I would love to hear why our assumptions don't apply to you. So this would be really great.
Gotcha.
Yeah, cool.
All right, cool. Thank you very much, Sam. I appreciate the conversation, and I'm going to go ahead and take you off the screen now. But please let us know the next time you have more questions. This was awesome.
Yeah. So Douglas asks in chat, are weights analogous to gas and ETH? And I guess the short answer is kind of yes. But I think gas is a little bit more arbitrary. Again, there is no. I don't think, from my understanding, that gas ever maps back to like computational time, like some kind of like tangible in the real world value. Whereas weights, we kind of do have this, like, it always at the end of the process maps back to like human seconds. But in terms of, yes, they both represent some kind of overhead. They both represent, they both are used to measure limits. They both measure computation, all that kind of stuff. Yes, that is the same. Okay. Let's see. So I haven't been cut off yet. Are people tired of hearing me talk? Because I guess the last thing I would want to do is maybe like just like really quickly take one of the, like, take a simple palette which doesn't have benchmarks, and then like really quickly maybe just set up what a benchmark might look like. But if there isn't time, I think that my presentation actually does basically what I would do here anyway. So I don't think there's a lot to be gained from having done this.
It's up to you, Sean. How long do you think it would take?
I don't know, probably another 30 minutes, but
if it's going to be 30 minutes, I'm actually personally going to request that we skip it, because I have more meetings and stuff today that I have to drink more coffee and get ready for and all that kind of stuff. Please don't forget to share the slides. Douglas is requesting a demo. I believe that I can drop off and you can still continue to present.
Sure,
but I kind of do need to it's only 9 o'clock here in California. I got to get my day started and everything.
Yeah.
Okay.
I'm happy to stay on. Yeah, I'm happy to stay on if people want to hear me talk.
Okay, cool. I'm going to go ahead and drop off then. Can you go ahead and share the slides before I do that, just so I can kind of do my due diligence and make sure that happens, or let me know if I can help make that happen?
Yeah, I'm trying to think what's the best way to upload a file. I shared it on Discord before. I'm going to share it in the Substrate technical channel on Riot. So if you're not in Riot yet, definitely go, and you can see it there. And then I'll also hopefully create a link. I probably just,
because I see you just uploaded the directly, and you can't do that in Crowdcast.
Maybe I can share this. Slides. Let me see. If I go to Google Drive, I can upload it, I guess.
Yeah, you can do it that way.
Do like.
And Sean, do you know what? I can go ahead ahead and take care of that. I can grab your slides from Discord and upload them to Google Drive. I'll do that after I drop off, and I'll let you continue with your demonstration.
That'd be great. Yes, they're already on Discord in the Sub-Zero channel from my section in chat. They're already there. The first comment in the whole chat.
Okay. All right, Sean. Thank you so much.
Okay.
right.
So yeah, so let's take a look at a palette now. I was thinking about pseudo because I think pseudo doesn't have any benchmarks in it. The problem with pseudo is that it's like so simple. It's like there's basically no components, there's no kind of overhead to worry about. But I think it's probably a reasonable enough example. Getting into anything more complex kind of gets a little bit more I don't know, complex, I guess. So the pseudo palette doesn't have any benchmarks, so let's go ahead and add that. What I would do is basically create a new file called benchmarks.rs. And this would be a module. And what I would do in the real world is probably just copy an existing benchmark. So I would look at something like, let's say, balances, benchmarks. I would just copy this file over here. And then I would just delete a bunch of stuff. I would just delete pretty much just everything. So let's just delete all of this. I just want to leave the template of a thing. There'll be a function called pseudo, so I'm just going to change that real quick. And then let's delete this code. Okay, let's delete this. Use create module as pseudo. Probably don't need this for now. Pseudo palette benchmarking, and then I'm going to delete all the other extrinsic stuff. Also, let me know in chat if it's not big enough, my screen, my text. Hopefully it's readable. And then there are some tests, so I will just get rid of these tests for now. Okay. So at this point, I want to save this. I want to, in my librs, I want to, of course, import this this module. So I'll have mod benchmarks. And then you'll see actually this benchmarks, it has at the top feature runtime benchmark. So this file, increase my font size, no problem, I can do it. This file will only get compiled if the feature runtime benchmarks is there. So which is why I'm able to just import it over here. You can see here that there's another way to do this. You can basically add a tag over the import, but in this case, I just have the file itself have this condition. So at this point, I just want to sanity check that this palette builds with the feature. So P, and I will actually have to update my palette to include this feature. So this will not work for now, but I will show you. So cargo build P, okay, I need to actually CD. So first thing I need to do here real quick is one of the problems you'll see is if I do cargo build.
Sean, I'm actually still here. I'm just about to drop off, but before I do so, someone is asking you to increase your font size, I did. Okay, cool. I'm leaving now, I promise. Bye-bye. Thank you.
And I do have chat window open, so if you're talking, I'm seeing it on another monitor. Anyway, so if I were to run this right now, and I were to run for my palette, p palette pseudo, I'm actually going to get into an error. And it says that features are not allowed in the root of a virtual workspace. So this is something very specific to Substrate, that the way we organize our project is a virtual workspace. The solution to this problem is basically just to navigate into the folder with your crate. So I would go cd frame pseudo. And now that I'm in the folder, I can then build, at this point, there's no p pseudo. I just build the crate itself, which is the palette. So cargo build features runtime benchmarks. So you see here, that this crate doesn't quite have the features yet. So it's not enough to just add this benchmarks file here. I need to actually edit my cargo toml file to support this new feature. So here's the toml definition for palette pseudo. And you can see here there's some existing feature definitions. One you're familiar with probably is this std. So we tell this crate how it can build using the std feature flag. So what I want to actually do here is introduce a new feature, runtime benchmarks. And when this feature is happening, we want to do some other stuff. Like we want to introduce into our crate the runtime benchmarks. So actually, I will go look at another file to get a feeling of what this looks like. So again, this is what I would recommend you do too. You can see this is optional imports for benchmarking. So this cha-cha I don't need, but I think this frame benchmarking I do need. So I'll copy this into my TOML file. So here I'm importing the frame benchmarking crate, but you can see here it's optional. So by default, we won't use this crate in the compilation. But what I can do is when we use the runtime benchmarks feature flag, I can add frame benchmarking, and it will then import and use this crate. So this is how we do features. And then, of course, you need also some stuff, like there's some other crates which themselves have the runtime feature flag. So if I take a look back at staking, I'm just looking at the cargo TOML file again. You can see here that, oh, I guess I don't need anything else. But you could imagine that, for whatever reason, you might want to do like frame system /runtime benchmarks. If for whatever reason you need to use the runtime benchmarks features of frame system, you can do that, or frame support runtime benchmark. So like there might be like certain trait definitions or function definitions which come from this feature flag. So you need to basically tell Rust that when you compile this pallet using the runtime benchmarks feature flag, it needs to also use the runtime benchmarks feature flag for the other downstream crates. So here's an example of kind of what I would expect. So now if I do build, I'll do it with the P because I can. Oops. No, it doesn't work. Okay, so just building the crate. You can see it's building, no problem. Hopefully it will get to the end. And that will show the basic setup that I basically added a new feature flag to my runtime. I introduced the unique benchmarking crate. And now I'm able to access this crate and this functionality. And you can see this frame benchmarking crate is what actually provides a bunch of different macros and tools which allow things to work. So from the frame benchmarking crate, I'm able to access this benchmarks macro, which is the main macro used to wrap all of the benchmarks. I'm also able to access this account function, which basically easily allows me to generate like an account, and this whitelisted caller, which is a specific kind of account who read and writes to this account won't happen. Okay, so let's see. There's a compiler error. This probably means I didn't set up my features perfectly correctly. So you can see here there's an unresolved import to SP core. So probably what I need to do is either potentially I need to remove. Let's see here, dev dependencies SP core. So probably I need to do SP core runtime benchmarks, my guess. Let's see what happens here. Nope, this doesn't work. So I wonder if I over committed these feature flags. Let's see what happens here. It could be that I introduced one of these things which we don't need. All right, so let's see here. Is no in the root. So I'm trying to understand. So this is a dev dependency. So my next guess is something like this needs to be default features false. Default features equals false. And then let's try that again. Let's look at another TOML file. See what's happening here with the core. Yeah, so here's SP core. Yeah, it doesn't seem like there's anything quite different here for this one. I wonder what's causing this issue. Primitives. Oh, I see. Maybe it's I need to do this. SP primitives dot runtime benchmarks. SP primitives is not a crate, so there's no SP primitives. It's let's just try SP runtime, right? And then we also have let's try SPIO. I don't think I need this feature flag. Sorry, y'all. This is real world though. This is real world, the kind of things that to figure out these dependency issues. Failed to. So this is also another STD issue here. See, I'm pretty sure it's one of these things I need to use let me see, frame support runtime benchmarks, and then frame system runtime benchmarks. SP core primitives API. So is it SP API? That would really suck if I'm stuck on this one issue. No, I think this is saying that there's no feature flag here. I wonder if there's a mistake somewhere here. Frame benchmarking, optional true. Frame system support, runtime, codec. I wonder if I run cargo test instead, if it will go away. Wasn't function. Okay, I'm not sure. I'm gonna go back to the benchmarking file because I feel like this is something that maybe I will figure out just from thinking about it for a little bit. But assuming this compiles, basically when we compile with this features runtime benchmarks, it would basically include this part of the code as a part of the benchmarking. And so basically what we want to do in the benchmarks, of course, is to test the worst case scenario. So again, we have to look back at our extrinsic and kind of understand what it does, and then we are able to write a benchmark for it simply, right? So here's the pseudo function. And so there's a basic ensure sign check. So this is a user calling this function. The user is inputting some call, right? Then there's a basic check, which checks that the sender matches something in storage. So we're definitely going to need to store ahead of time that the account that we're using is the pseudo key. Then we're going to dispatch the call, right? This is actually kind of a complex thing because this call could be arbitrary. We could be doing it into different extrinsics. And as a result, the weight of this entire function could change a lot. And I'll show you a trick to this later. But there's going to be dispatching a call, and then we're going to deposit an event. Okay, so it's pretty straightforward. So basically, the main part of our benchmarking setup is basically going to be setting up that this sender is the key, that this sender is stored as the pseudo person. And the thing that we're going to say that this benchmark is going to depend on potentially is the size of this call. So again, this call input could be of kind of different sizes, right? So depending on the size of this call, the overall benchmark itself may take longer just to process, for example, the call, to do different stuff with it. So that's what we're going to get with the benchmark. So we'll say that this function. Let's go here. That this function is a function, has that one component. The component is the length of the call. So we'll say let C for call in 0 ... something like t t max call size get. And this basically allows us to have a variable which adjusts the size of the call. This max call size doesn't exist, but something we could create, or we could look at Substrate. Substrate has a max block size, so we could probably use that too. And that limits the size of any object in the Substrate block. Okay, so we have this basic variable. Then we want to basically set up an account. So we can do something really simple: is say let caller equals whitelisted caller. And again, this is a special function we inputted from frame benchmark. And this uses an account whose database operations will not be counted for when we run this extrinsic. So things like taking the fee from the user or things like updating the nonce, that would be database operations. But for this account, we just give that for free because this is part of the requirement for any user to basically make a signed call. So this is the caller we're working with. So in order to set up our state correctly, what we need to do is actually put this caller into storage. So remember that there's a keys variable. So what I would do here is basically just say keys t put caller. Probably need to clone it. Just something I know ahead of time. And this will basically put this caller into the storage so that it is sudo. Now, this is a kind of direct way to do it. You could, if you wanted to, call an extrinsic. Like you could call sudo t, or there's probably no t here, but sudo like set sudo or something like that with the user, and whatever extrinsic it would be to set the sudo account. So yeah, set key is this function, and this would be running the extrinsic, which ultimately does just call key put, right? But there might be some other logic in here that you want to execute, or there might be some more complex storage being manipulated here. So rather than just directly putting key put like I'm doing, I could call sudo set key, raw origin root caller.clone. And then I would basically make sure that this completes successfully. And if I look real quick, I'm basically just directly calling set key, the origin. Oh, I guess that needs to be a signed key. So this would be a little bit of a problem with that. But anyway, it needs to be the sender, and it would be the new account. But for us, we don't need to do that. We can just put the key directly in, save some time, and save some trouble. So now the one thing we need to do is we need to create a call, right? And this call needs to have variable size. So the hard part about this benchmark is going to be, okay, well, what are we going to do? This sudo could call anything from a balance transfer. It could also call a runtime upgrade or whatever, right? And those are very different weights. So what we will do in our benchmark is we won't attempt to measure the weight of the call it's calling. Instead, we will take advantage of this. You can see here we're kind of hinting at it. This call get dispatch info weight, which basically will give us the weight of the call we're making. So what we want to do is actually benchmark the pseudo call, where the call we're making is a no op. It's basically it does nothing. It's just a simple does nothing call. And what we can actually do is take advantage of the system palette. So the system palette has a call. So I'll say let no op equal system, so I'll say frame system call t remark, and this remark will have an input of bytes. And if we take a look real quick at the system palette, this is just an example of how we do our no op transactions. The system palette, if I go fn remark, has this function here where the only thing this function does is call ensure signed. And otherwise, it takes this random arbitrary blob of bytes and does nothing. And so this is, for the purpose of the benchmarking, our no op operation. This has basically no tangible weight associated with it, and it's just we could just use it as our tool for benchmarking. So in our benchmark, you can go ahead and basically say this no op is this frame call. The other thing that's nice is that we can control the size of this call using this bytes. So I can say here, let bytes equals vec, and I'll put just a 0 byte. It's a 0 U8 of length C. So this will generate some byte vector with the same byte, this 0 byte, of length C, which is the size of the call we want to test. And so then when we create this no op call and we're passing in the bytes, this bytes here, we're actually making the size of the call the size that we want. And then at the last point, we just need to basically make this call. So you can see here actually from the last thing I was copying and pasting, I already have some code here, but I'm just going to clean this up. But this is the more normal way you might expect a benchmark kind of signature look like, where basically the input here is exactly what the input of the extrinsic would be. So the first input to the extrinsic is the origin, and the second input is the call. So I'll put no up. Okay. And then a verify statement. Is there something we can do to verify that our call was successful? Yeah, there's an event suDID. So what we can do here in our benchmarks, and I won't do it right now because I want to see if I can get the compilation fixed. But like at the very end, we could verify that this all ran by looking check suDID event fired, right? And so let's take a quick look at the syntax. You can see here, again, this is all macro magic. So this is not real Rust, but this is kind of a syntax I think is hopefully understandable. This is a benchmark for sudo. And we know that because up here it's called sudo. But this could actually be any string you want. We call this benchmark for sudo, right? So you can name your benchmark whatever you want. This is useful to be able to name anything you want. If you have like sudo path 1, and then you might have another benchmark, sudo path 2, another benchmark, sudo path 3. You want to actually benchmark the exact same extrinsic multiple times. But if we only want to benchmark a single thing, we can have sudo here. And you can see there's a syntax here with this underscore, where we're basically assuming the name of the extrinsic we want to call is the same as this name up here. So if we were to do up here benchmark for sudo, we would have to change this underscore to be called sudo. And then here is where we say, okay, well, we're calling the extrinsic sudo, and here's the function, basically the function signature for that, right? As I mentioned, you don't even have to do it this way. We could, if we want to, if we want to get really hardcore, have basically dispatch any random logic we want. So this is the format for a normal extrinsic that we kind of expect using frame. What we could also do is let sudo call equal pallet sudo call t sudo with the inputs of the same here, right? And then we have just a normal call here. And instead of doing anything like this at all, we could actually, instead of using that, we add new brackets. And then in here, we can write any logic we want. So we could write something like sudo call.dispatch. Actually, in this case, sorry, we do not need the raw origin. Sorry, the function signature, when doing it this way, the call doesn't include the origin. This is why I didn't include the origin here. What we do is just include the parameter that we want, and then we do dispatch with the raw origin. And so this would be exactly the same thing. This is actually in the background what the benchmarks does in that little special syntax. But you can also do other things here, right? I could do for just a for loop in here for I in 0.100, hash I, right? Like if I wanted to benchmark what 100 hashes are, I could just run this as my benchmark, something like that, right? Or I could run any logic I want. You can wrap anything you want into this kind of generalized closure statement, basically. But for our purposes, again, the average scenario for us is to write just a simple extrinsic, which will have just the one name. It will have the inputs we want, which will be raw origin, signed, caller, and then this no op. We don't need this anymore. And then our name of our function should be sudo. So at this point, I would like to brainstorm how to get this compiling, because gotta be a real bummer if I just get blocked on this one import. Pub use. Let me look at what this is complaining about. So this is configured not feature std. And this is SP API. So I think there is some kind of leak happening in terms of the no std stuff. So let me go back here into our sudo. Where did it go? Sudo. Let me play around one more time, because I feel like it's this SP core, right? It has to be this SP core. So I'm going to assume it has. Oh, the staking has SP core too, though, right? So SP core. Yeah, and default features std. all these SD. Let me double check that this cargo file looks right. So Surday, yep, codec, SP, IO, SP runtime frame support system. Yes. Default features false. Based off of the other one, this does not look like it's needed. Let me look at another crate real quick. So another one that has benchmarks is scheduler. Has a cargo toml file, which also uses SP core, but this one has default features false. Let me try this. Let me try the default features false. Cargo. Okay, let me try one more thing. Sanity check. CD. Oops. What was I? CD substrate 3. CD bin node CLI. And let me try this again. Oops. Cargo build package pallet sudo. Let's see what happens here. So in this case, I moved out of the sudo folder. I moved into the node folder. And it could be, the way that features works, it like picks up features from all the other crates. So I'm wondering if somehow the node folder has some correct implementation that would solve this. And actually, probably what I need to do, and probably what I haven't done at this point, is in the node folder, I need to introduce the runtime benchmarks for sudo. So I'm going to go to the bin node runtime source, and then I have a cargo toml file here. And you'll see that in the node runtime, this is where you set up your construct runtime. It did finish compiling, which is good, but I think I need to make sure that in here I also have a line for pallet sudo runtime benchmarks. And this basically says that when I compile my runtime with the runtime benchmarks flag, also compile pallet sudo with that flag. And this is where I think maybe it's going to give me a headache again, but hopefully not. In a second. If there are any questions while I'm doing this, now's a great time to ask them. Oh, this is great. So it looks like it did compile. So there definitely is some kind of cargo problem with the sudo cargo toml file. I'll figure that out later. But you can see here it is now actually looking to compile my code, and it's telling me some errors, probably just some basic stuff. So failed to resolve type or module keys. So probably what's happening here is I have not imported the keys storage item, or either that, or it's not named keys. It's probably just named key, probably just one of them. Let me just make a guess here, Yep. Okay, and then of course account is not being used. This line isn't being used. I'll just remove these because they're warnings. Okay, so this max call size isn't being used. So for now, I'm just going to put a random number in here. I'm going to say 16,000 bytes is the maximum. But what you should do in practice, of course, is to have something configurable which limits what the call size is. And again, I would recommend maybe actually, and we can actually just do this right now, I think. I would look at the system palette. I think system palette has built into it. Let's go trait. It has into it maximum block weight. That's not what I want. Maximum block length. See here? They have the maximum length of a block in bytes. So this is, I think, what would be a practical size to use. What I can actually do here in my benchmark is put t maximum block, what was it? Block length. Get. Let's see if this solves that problem. Okay, so give caller a type. Okay, so caller is an account ID, T account ID. You'll notice that in all the benchmarks, that we get access to T, just like you would expect for everything else. Basically, this trait, we wrap that all in the benchmarking framework. Didn't I save this? No, I didn't save it. Okay, expected use size on Unit 32. That's simple. As use size. Okay. Oh yeah, this question mark doesn't make sense. We're not executing this call. We are basically this is actually an enum. It looks like a function, but it's actually an enum that we generate when we generate all the different pallets. We generate for each pallet an enum of all the different functions it has, and the values inside the enum are the parameters for that function. And this is how we do function dispatch. So this is actually just an object, it's a no-op object. We pass this into the call. So let's do that. Okay, box. So I think I need to box it. So I can do box new. No problem, Rust. I will be your friend if you let me. Oh, and then finally, probably I need to do like an into statement. So it's expecting a generic call, and I'm passing it a system call. And basically, what we do is we automatically implement for you in declare module. Not only this enum, we also implement for you a way to transition between the calls, the specific pallet call type and the generic runtime call type. And the runtime call type includes all of the things. Oh, it's not implemented. Okay, so let me take a look real quick at the trait definition. So here, call is defined as this. So actually, one thing I would need to actually do to update this palette to make it so that I can benchmark runtime better. There's a few ways you could push this, but I think I need to implement from frame system call. I think this is what I need to do. Frame system call self. Okay, great. And so what this did is it basically added an additional trait bound. I said that, so this palette expects some kind of call type. And this call type has to have these traits defined. Like it needs to have parameter. It can be a parameter of a function. It has to have unfiltered dispatch, so it can be dispatchable. So it is a dispatchable function. You can be able to get dispatch info from it. And then here I'm saying that whatever the call is, you should be able to convert it from a frame system call. So basically I'm saying that all calls will at least have the frame system calls, which is a reasonable assumption to make for any palette built using frame, because all frame palettes use frame system, right? And so with that, I'm able to convert this frame system call that I want into the generic call type that it expects. Okay, and so this works. It compiled. I didn't use this const seed. That's fine. I can get rid of it. Okay, and it compiled. So now I want to just do a basic test to make sure that my thing runs correctly. And to do that, I want to write a verify statement. So to do that, I'm gonna copy a small code block, which is something we use a lot. So I'm gonna search last event. And I know in other benchmarks we have this function here, assert last event. And this basically will allow me to make a quick search. I'm going to copy this right into my runtime. I'm going to get rid of the function signature a little bit because we don't use instances in sudo. So I need to get rid of this I statements. Any more I's? I think that's it. Okay. And then basically what this does is it allows me to assert the last event was something. So if I look at the sudo file, it was something like sudid, right? Let me make it into the other window. we have here at the end of sudo, it deposits event, raw event sudo with a result. Either it'll be okay or error. And of course, we want to make sure that it returns the result okay, so that we know that our action is fired successfully. So what I will do here is use assert last event. I will say assert last event, raw event sudo with the okay. And I think I need to put dot into here just to make it all happy. Oop. Okay, so a few things I need to import. So I need to use frame system event record. Anything else? Expected enum result found. So I think instead of just that, I need to do okay with stuff inside of it. System not found in scope. That's fine. I can just change this to frame system module. Let me close this. I don't need this anymore. So last thing is that assert last event is generic. So I need to add a T here, and that's no problem. See, Rust is telling me the answer to all my problems. The Rust compiler is your friend. Okay, and this is compiling. Great. So to test, so before I actually compile my node and run this benchmark, I want to test that it works in the general scenario. So we have some tests down here. So as a part of this benchmarks macro, we actually generate tests for you. And the tests are named something like test benchmark, and then like sudo. So it would be the name of your palette and then the test benchmark in front of it or something like that. Let me actually look at the README. I think that I talk about it here. So if you look at this is the, if you go to frame benchmarking readme.md, there is a nice file I've written about benchmarking. And if you look at tests, yep, it's test benchmark name, and then all that stuff. And if your benchmark is successful, it'll return okay. So I want to do a new test. So I'll put up here test fn test sudo, or I'll just call it sudo. Why not sudo? And then this function will do one thing. So actually, just like any other runtime test, I need to set up the mock environment. So I'll see here from the tests, this new test externalities is what I will run. So I'm going to copy this from there. And this basically sets up my like mock environment, the new test externalities. And then within that, let me close this. I will run assert. Okay. Test benchmark sudo. No, it needs to be T, right? T. I think that's it. Let me just take a look at my docs real quick. Double check. Yep, test benchmark T. So, and actually this can't be T, it has to be test. So in this case of me running the test, my runtime is this test runtime coming in. So this is exactly what you would do with any other benchmark or any other runtime test. You would basically pass in your test runtime. And this tells my runtime, my benchmark, basically what runtime to use. So let me see if this compiles. So I'm going to do cargo test p pallet sudo. Okay, a few little errors, no problem. We can fix this together. Test composite. Yeah, I think. Oh yeah, this is not right. This is just test. That was from copy paste before. Let's see what this says. No X builder in tests. So probably. Nope, maybe we don't need X builder. Why do we need X builder? Do we use it? Nope, we don't need X builder. So let's just get rid of it. But we do need new test X. which is a function. Test is a private struct import. So I want to make that pub. So in test, this is all coming from mock. Okay, so maybe what I'll do instead is just import it from mock instead. Mock, and that's probably where all this stuff is coming from. So call is not implemented for mock call. Okay, so in order to solve this problem, so this is saying that in my mock environment, I'm not satisfying this trait. And this is probably because I haven't, the mock environment doesn't correctly set up the calls stuff. So let me look here. So what I need to do to make implement outer dispatch. What I probably need to do is just in here, this implement outer dispatch, I need to also include frame system. Frame system. I think this is all I need to do. So remember, what's happening here is that our macros in frame are doing a lot of work for you, like a lot of work. So when I say something like in this librs file that this call type needs to be able to do from system call, basically like this is a conversion that you would otherwise need to manually define. You need to define how exactly we convert from a frame system call into our generic call type. But these are things that we take care of for you when you run our macros. And so you probably you would never have seen this macro implement outer dispatch unless you've written tests or whatever. This macro actually exists as a part of the declare module macro. So declare module has a bunch of lists of all the extrinsics, all that kind of stuff. It does some expansion. And at some point it implements this outer dispatch, which basically is implementing an enum call with a list of all of the calls of all of the different runtimes, and it implements all of the traits for from and into and whatever. So the problem I was running into at that one point was basically that I had this trait definition, but I did not implement this trait. And this is something that you would normally not have to do. And the way I solved it was basically I made sure that my mock was correctly doing it for me, automatically doing it for me. Okay? So once I solved that problem, my trait is now satisfied. And look, the tests run. And it's all green, it looks like. Oh, no, failed. I said that too early. Oh, we see here. So that there's an error, that the dispatch error, it's a bad origin. Okay, so let's look at what could cause that. So I have a feeling, what am I feeling here? I have a feeling, oh yes, there's a problem here. The problem here is that sudo dispatches this call with the root origin, but my no-op call that I was trying to use, let's go back to the system, the remark expects a signed origin, and that would make it so that my call wouldn't satisfy that. Now, to be practically speaking, the pseudo call doesn't have any other logic beyond just firing the extrinsic. So the fact that this failed is actually not does not mean that my benchmark is bad. Like technically, this would actually still work as a good benchmark for this palette. But I think the solution to this problem would basically be to use a extrinsic which needs root. So look at this. Like look at this function here, fill block, right? Or we have another function here, set heap pages, also a root origin or something like that, right? Here's one, set code. Yeah, actually, I probably would call set code without checks. No, I don't want to call that. I guess the easiest thing to do to do this test the way I want to do it is actually to create a new remark, a new extrinsic here. Basically, you would want to be able to make sure that in your situation you have the correct setup that you need to benchmark your system. And this might involve creating a new function. So here, I'm going to do remark root And actually, at this point, I need to even call it remark. I just call it no-op. No-op root is some function in a pallet in frame system here. And it has the exact same signature. I'll just call this, instead of remark, I call it bytes. And instead of ensure signed, I'll do ensure root. Okay. And so this will pass the check, and this will be what we use for our benchmark. Now, this won't be something I commit to Substrate, but this is just to give you an idea of what's going on here, right? So let's go back to our benchmark. So instead of calling remark, I will call no-op root. Is that what I called it? Geez, I wish I could even remember what I did 3 seconds ago. I called it no-op root. Okay, I shouldn't doubt myself. And then this should work. Not found in the scope. That's no problem. I just shouldn't have changed this name. I will just change it back to remark. But here you can see that, by basically by taking advantage of the test generated for me by my benchmark, and by adding this verify statement, this assert statement, I was able to find that there was a problem with benchmark. I fixed it, and now you can see all of my tests pass, including my benchmark. So now we have a good working end-to-end benchmark. Okay, at this point, I might want to actually run this benchmark, right? So I've written it in my palette. I might want to actually execute it in my node environment. So I already kind of hinted above that first thing we need to do is actually add this palette and actually add the benchmarking for this palette into my runtime. So the first step here was basically this palette already existed in my runtime. I needed to add to the runtime benchmarks feature flag to also use the runtime benchmarks feature flag of my palette. So I added this new line, palette pseudo runtime benchmarks. Great. The next thing I need to do is in my runtime itself, there's a big definition here with all the stuff. If I look for it, there's this add benchmarks. And there's this block here. And this is also behind the feature flag runtime benchmarks. And this implements basically the utility of actually running a benchmark in my runtime. And you can see here, there's some configuration. This gets pulled from the CLI. There's the whitelist. This is the whitelist I was talking about. You can see here in this case, the whitelists are hard-coded keys. These are hex keys that we know for sure are good. But you can, as I mentioned in my talk, that you can go ahead and adjust the keys such that you're pulling them from the declare storage API and stuff like that, right? And then you can see here, I have this macro add benchmark. And this is pretty simple. So you can see here, we've added all of these benchmarks to our runtime. So I need to add a new one. I need to go here, basically copy this line, add benchmark param palette pseudo is the name of my palette. And then the object, the name of this object in my construct runtime is pseudo. And I'll show you this. So if I go to construct runtime, you'll see here I am in the construct runtime, it is imported as pseudo. So that's what this name comes from. So this object name here. And I think it's as simple as that, to basically add a new benchmark to your runtime. And this entire all this other code is actually already included with the node template. So it should already be in your runtime if you with all the benchmarks for the node template there already. So at this point, I'm going to rebuild the node. So I'm going to build my node, cargo build release, but now with the features runtime benchmarks. And this is going to take a little bit of time to compile. We have any questions, anything? There are at least a couple people watching. That's cool. Everything so far makes sense, hopefully. For clarification, the TOML file is a configuration file for Rust. Yeah, so that's just it's the same thing that every create package uses. So I think you can think about package.json in Node.js. The equivalent is like a cargo TOML file in Rust. Yeah, but adding a benchmark is this simple, and this is again a lot of macro magic, a lot of work to get this streamlined. But you can just pick and choose which palettes you want. Yeah, everything is extremely easy. Yeah, and to be fair, everything does look extremely easy. because I picked a very easy extrinsic. As you get to more complex extrinsics, obviously it's going to be more complex benchmarking. But what I would say is this, that the person who writes the extrinsic is probably the person who writes the benchmark. And by writing the extrinsic, you already know how your extrinsic should work. You already know the limits of it. You already know how it functions, right? So it's a joke. It's not very easy. Okay, well, I don't know. So you do know how it works. So it should be, no matter how complex your system is, pretty easy to write benchmarks. Especially this, that because benchmarks look just like tests, as long as you can write a test for your extrinsic, a good test for your extrinsic, you can write a good benchmark. The only difference is your benchmark is a test for success on the worst case scenario. Okay. We're still waiting. Just let's chill a little bit. Polls. Okay. Let's see. What else do I want to talk about? Yeah, there's a lot of features on benchmarking. So again, I definitely think over time it's going to continue to evolve. There are already a few kind of breaking changes I want to push in terms of how the benchmark macro works and how the actual output of the benchmarks file is and how we set things up. But nothing radically is going to change about the process, or nothing radically is going to change about you writing your benchmarks. So I would say that just give benchmarking a little bit of a leniency in terms of you having to maybe maintain some code with some breaking changes that we might push. Okay, 60 out of 62. We're getting there. So what I'm going to do here is, after I've compiled this node with the runtime benchmarks feature flag, I'm going to execute this new benchmark I created. And we're going to see kind of that whole process. And so there'll be a command line thing that I need to pass. So maybe I can start preparing that. So basically, you can see also in this documentation has an idea of what we want to do here. So again, we want to make sure that we're executing with WASM. We want to make sure that it's compiled, how many steps, how many repeats, and we're going to output the file that we're doing the benchmarking to. So so actually maybe I can do this in another thing. So what I can do here is do target release substrate, use the benchmark subcommand, chain dev, execution equal WASM, WASM execution equals compiled. I'm just basically copying this stuff, but this is different. Pallet is pallet sudo. Extrinsic is transfer, or not transfer, sorry, is sudo. Steps is 50, why not? Repeat is 20. So I'm going to do, so remember, we have between 0 and maximum block length in terms of size the blob we're passing. So we're going to be doing 50 samples across this range to get an idea of the curve. And we're going to measure at each sample point 20 times the same exact thing to get an even measurement of what that one thing would be. And then, of course, we want to output this all to, let's say, the current directory. And also, I can add here a raw, which will show me the raw output of the benchmarking process. So we can take a look at that, too. I can only run it once the binary is finished compiling. It is. OK, it finished compiling. Great. And so now if I run this, it should just work. Oh, if I can also spell correctly. Extrinsic. Nope. Oh my gosh. Extrinsic. Yep, okay, it's running. Great. Let's see, it's running, takes a little time to think. Okay, and then we have a bunch of output. So let's take a look at this. So with this raw flag, I basically, you see the time, the number of DB reads writes. Like this is all the raw data. I think at the very top there is oh, I can't even show you because it has too much. Actually, what I can do here is I can output this to a file. So output.txt. And if I look at this output.txt, you see here, yeah. So there's an output file, and here the first one is the component, the component that we're measuring. So it's C, the extrinsic time, the storage root time, the reads, repeat reads, writes, repeat writes. And so you can see here, first we're measuring 20 times with C equals 0. Then we measure 20 times with C equals 100,000. Then 20 times with C equals 400,000, et cetera, et cetera, et cetera. We measure this 50 times across the sample, and you can see here the time it takes. So you can actually crunch these numbers through some kind of graphing program to see all the graphs. What we also show you in the output, let's get to the very bottom of this output. We also show you the analysis. So this is the raw data, but more importantly, we want to show you the analysis data. So here is the mean slopes analysis. So here is the approximation of this function given the mean slopes analysis. We also have min squares analysis. And you can see here read and write functions. Like these are all these different functions that are generated. You can see here distributions. Like this is all the analysis work we do in the benchmarking framework. And so this stuff then all gets converted into this file. See, there's a file that was generated called palletsudo.rs. And this is a file which defines a weight function for pseudo. We can see here that the C variable, the size of this call, actually didn't affect the execution of the call. And that kind of makes sense, right? Like we weren't actually doing anything with the remark bytes. So here the C is not included, it's not even needed. But here we do have a base weight of a pseudo call. And we see that when you make a pseudo call, we do one read. And we know this read is the check to read is the user, the pseudo user. So all of this was automatically derived for us. And this is all wrapped within a weight info trait. And then we could just include this trait into our runtime. So let's go back to pseudo. I'm going to kind of cut corners here a little bit because I don't think y'all need to see at a super level. But basically what we could do here is we could define in the pseudo palette a new weight info trait. So I'm going to have here trait weight info. And this is going to define the functions we need. So here I just have one function, pseudo, which has a component C, which is the U32, and that outputs a weight. So this is my trait. I want to make it configurable. So I, in my my configuration trait definition, have a type weight info, which is weight info. So basically I can allow you as a runtime engineer to configure what the weight info implementation is for this. Then I would, in my function, let's actually remove this line for now. I'll comment it out. So don't look at that. But I would define a new weight function. Weight equals t weight info pseudo. That's the name of the function. And the input would be the length of this call. So it would be call.len. Now, what we're missing here, though, is that this is the weight of the pseudo function. But we have to also include the weight of the call we're dispatching. This is something very specific for something like pseudo or any of the other functions we're dispatching another call, where this call triggers another call to happen. So what I would actually do to make this safe my runtime is actually on top of this weight info pseudo weight, I would do dot saturating add call dot get dispatch info dot weight. And so here, basically, I'm taking advantage of the fact that this is a call, and this call will also have a weight definition. And what I can say is that this overall pseudo call will be the weight of the pseudo function calling a no-op call, calling nothing, plus the weight of the call itself. And then these two weights added together is the overall weight of any call coming in. And of course, this weight is dependent on whatever the call you're making is. So this would be the weight of pseudo. And then the last thing I would do to integrate all of this is basically once I've updated the signature of sudo in my runtime definition, my bin node runtime source. Okay, I have here a definition for the pseudo trait. So pseudo : trait. Yep. I need to, of course, define here a new weight info, type weight info equals, and I can import the struct that I defined. So I will import from here weights pallet pseudo weight info runtime. Actually, I don't need this colon, just like this. And to get this, you'll see that this is saying that there's a module weights. This module weights has a module pseudo, and this pseudo defines this struct weight info. And so if I look at the runtime, I have this folder weights. This folder is a module, and this has a list of all the different weights I have. I'll add a new weight here. So I'll add here pub mod pallet pseudo. And then I will copy this pallet pseudo file that was generated just right into here, right into this folder, this weights folder. And then basically now I have access to this weight info struct, which defines the pseudo function. And then that's it. So now that I have a weight definition here, which through my runtime configuration gets pushed into the pallet to define what the weight of that pallet is. And that is the full end-to-end benchmarking, what it looks like. So that's pretty much where I'm going to leave you at. I will spend just a moment to see if there's any more questions, if anyone's listening. But hopefully that gives you a good idea of kind of the end-to-end scenario for kind of how you do weights. As you can see, a lot of these steps I've done here can be automated because the file gets generated. You can just basically, once you've set up the pipeline of your runtime to use this weight info, you can basically just have the bot automatically push updated weights to this folder. But yeah, okay, there's a question. Is there a way to do this without all the mucking about in Rust or Rust templates for this function for a pallet? So Rust templates for this function for a pallet. So I would say this, that there is no way to get around doing the setup once. Like you're gonna need to update your TOML file to have the feature flag. You're gonna need to write the benchmarks. You're gonna need to add this weight info trait. You're gonna need to do the basic stuff, the basic piping of the end-to-end process. But once that's done for you, then maintaining your weights is dead simple. It's just basically updating this one file, which is exactly generated for you through the benchmarking pipeline. So that is all that. In general, if you're not writing pallets, but if you're just building runtimes and building blockchains, a lot of the complex stuff is already done for you. All you need to do then is just define this part here, that all the other definition of the actual weight info stuff and etc. is all already done for you by the pallet developer. But yeah, there's no way getting around this stuff. Like, I mean, I think that it's possible that in the future we will introduce more macros, which could automate some of the manual steps. But the more macros we introduce, one, the more complex our system gets because you have to understand our macros, not Rust, right? And then also, the more macros we introduce, like the more breaking changes there are, and the more whatever. Like in general, I think this is not asking for a ton, especially since it's a one-time cost. It's not something you have to constantly be changing and maintaining. Yeah, hopefully that answers your question. All right, and another question is, so benchmarking is just kind of for performance test. So benchmarking is not just performance test. This is actually a safety test because when I have a block, you might ask, how many pseudo transactions can I fit into a block, right? This end-to-end benchmarking tells me a number which says the pseudo function costs this much to execute. And when it costs this much to execute, you can only run this many in a block. And again, as I mentioned much earlier in the conversation, making blocks that are too big can be a concern for the safety of your network. So really, in the end of the day, this is a security measurement for your blockchain. And when you're launching a new production level blockchain, you need to make sure to run weights on your assumptions, using your computer, using your assumptions of what your system should be. such that you get new weights for your system. So you can see here in this folder, real quick, there's a weight file for every single pallet. And you can see here there are hard-coded numbers. These are the numbers which are safe for our substrate chain in our substrate assumptions. The way that it will work for every single blockchain is every single blockchain will have their own folder with their own weights looking like this, but with probably different numbers, right? And you will use your weight definitions on your blockchain to keep your blockchain safe. And the whole point of this entire pipeline is that the pallet itself is flexible. All of the concreteness of what a weight actually is defined at your blockchain runtime level, and that's okay. Just like when a pallet for balances doesn't define what the existential deposit is, but your runtime must define definitely what the number is. And it's the same here. So this is the same principle we've been following the whole time. Okay. I think there aren't any other questions, and I have been talking for a long time, 3 hours now. So I'll leave you with that. Definitely ping me on Riot if you have other questions. The Substrate Technical channel is a great place to learn more about this stuff. I'm sure there are more things we can do, but the best way to learn about benchmarking is one, to review some of the documentation, review this my presentation, review this video, but also to look at all the other benchmarks. There are over 10 or 15 benchmarks end-to-end written for these pallets in this frame folder. Just learn by example. If you have a question, how would I do X? Go look at the pallets, and you can go look. My handle on Riot is just Sean Tabrizi. And yeah, you can find me. I mean, you can find me really quickly. I'm talking all the time in the Substrate Technical channel. So anyway, thank you so much for listening. I'm going to leave, and hopefully that will just end the stream. Okay. See ya, everyone. Mm-hmm.